Hello, and welcome to Sleep Gravity. Imagine a very quiet evening, beginning not inside a room, but with the ground beneath our feet. Earth is still turning steadily through the vast darkness. The oceans continue to rise and fall with the tides, clouds drift across the continents, and far above the atmosphere, the moon, the planets, and millions of small pieces of rock quietly follow paths that gravity traced long ago. Most of these motions are too slow for us to notice in an ordinary moment, yet they never stop. Even when every sound around us begins to fade, the solar system remains like a great house gently turning through space, with the sun at its center, the planets circling around it, and distant regions filled with dust, ice, stone, and the memories of an ancient time. Within that enormous home, nearly everything we know is connected to the sun in some way. Earth formed from the disk of material that once revolved around our star. Mars, Jupiter, Saturn, the asteroids, and distant comets all carry part of the same shared history of the solar system. They may differ greatly in size, temperature, color, and fate, but they still belong to the same gravitational family, held together for billions of years by the light and mass of the sunday. So when a small object appears in the sky and follows a path unlike those of these familiar members, science begins to pay attention. Not because it shines brilliantly or seems frightening, and not because it arrives like something strange from a movie, but because it moves through the solar system like a visitor. It does not circle the sun like an ordinary comet. It does not remain here to become a lasting part of this home. It simply passes through, receiving a little sunlight, allowing the ice on its surface to begin stirring awake, and then continuing outward toward the space between the stars. That visitor is called 3I, Atlas. The name may sound dry and technical, but behind it lies a much larger story. The letter I tells us that this is an interstellar object, meaning it was not born in the solar system. It came from somewhere else, from another star system, or at least from a region of space that no longer belongs to our Sunday. And what makes it even more remarkable is that signals, detected by telescopes, suggest its material may be extremely ancient, perhaps old enough to have existed before the sun itself began to shine. This does not need to be understood as a warning. 3I, Atlas is not a danger approaching Earth, nor is it a mystery that needs to be exaggerated into something beyond science. It is more beautiful when seen for what it truly is, a small fragment of ice and dust passing through our region of light after a journey so long that imagination can barely follow it. For most of its existence, perhaps no one saw it. No sky gave it a name, no planet held it in place, and no star remained close enough to make it a familiar part of an orbit. Then, during one brief moment in cosmic history, it passed through the solar system, close enough for humans to detect, within the thin gas surrounding it, traces of a place very far away. An interstellar comet like this does not speak through sound, nor does it tell its story in the way people do. What it carries is written in light, in water vapor, in carbon dioxide, and in chemical ratios, so subtle that only highly sensitive instruments can detect them. As sunlight warms the ice on its surface, some of the material that had long rested in darkness begins to evaporate, forming a faint cloud of gas around the nucleus. That cloud becomes the page telescopes are able to read. Each band of light, each absorption feature, and each molecular component is like a fine trace of ink left behind by the place where this object first formed. When considered more slowly, the event feels almost gentle. An ancient object does not need to collide with Earth, create a brilliant display in the sky, or remain for long in order to matter. It only needs to pass by at a moment when humanity has developed instruments delicate enough to recognize it. In the distant past, if a visitor like this crossed through our region, it may have disappeared again without anyone ever knowing. But this time, among the familiar orbits of the planets and the ordinary rhythms of life on a small blue world, we noticed a piece of matter that did not belong to our family. And from here, the story becomes deeper. because the question is not only that 3I, Atlas, is passing through the solar system. The question is how we know it was not born here. To determine whether an object belongs to the solar system, we do not need to see it looming large in the sky. Most of the time, astronomers begin with nothing more than a tiny point of light, sometimes so faint that it nearly disappears into the background of stars behind it. In a single image, that point may reveal very little. It is simply one weak speck among countless others, resting in a region of sky where the unaided eye might notice nothing unusual at all. But when several images are placed side by side, taken a few hours apart, then a few days apart, and across several consecutive nights, the point of light begins to reveal something more important than its shape. It is moving. Motion is one of the ways the sky tells us what is near and what is far away. True stars lie at such immense distances that, over short periods of time, they appear almost motionless against our sky. An asteroid, a comet, or some other object in the sun's neighborhood, however, will drift gently across that background like a grain of dust sliding over a pane of glass, while the lights beyond it remain fixed. This slow movement allows automated survey systems to detect objects that human observers could never track manually night after night. The sky is too vast, filled with too many points of light and too many subtle motions. Modern science therefore looks upward not only with curiosity, but with sensitive cameras, image comparison algorithms, and archives of data that continue to grow without pause. This is how 3I, Atlas, entered the story. It did not appear as a brilliant streak that made the whole world look up, nor did its discovery begin with a dramatic sight in the night sky. It first appeared as a faint point of light recorded by a survey system, a small signal within the familiar stream of observations gathered by telescopes designed to search for objects near Earth. The Atlas system, built to scan the sky and detect bodies that might enter our planet's neighborhood, captured its trace. At first, the most important question was not where it had come from, but where it was, which direction it was moving, and whether its path matched those of familiar objects within the solar system. In the hours and days that followed, astronomers began a patient kind of work. They did not study only the first discovery image. They also searched through earlier observations to see whether the object had unknowingly appeared in other photographs before anyone recognized it. This is one of the most beautiful aspects of modern astronomy. Sometimes a new discovery is found not only in the moment when we first see something, but also in the act of returning to old archives, reopening earlier data, and realizing that the object had already left faint footprints before it was ever given a name. Each recovered position is like a small stone placed along the course of its journey, and the more stones we find, the more clearly that path begins to emerge. Once those positions were connected, the real question began to take shape. If 3I, Atlas, were an ordinary comet belonging to the solar system, its path would have followed some recognizable form. Its orbit might have been extremely long and highly elongated, carrying it far beyond Neptune before returning thousands of years later. Or it might have followed a shorter orbit, like many comets observed before. But whether long or short, if it belonged to the Sun, the Sun's gravity would still have held it within a broad cycle of departure and return, a path that remained closed in the larger sense. With 3I, Atlas, the first calculations showed something different. It was not simply approaching and then turning back like a distant member of this home. It was passing through. We can imagine the Sun as a vast gravitational valley in space. The familiar planets and comets are like objects moving within that valley, sometimes farther away, sometimes closer, but never escaping its hold. A very distant comet may take tens of thousands of years to return, yet as long as the Sun still keeps it bound, its story remains part of the solar system. 3I, Atlas, is more like a small stone arriving from beyond the valley, rushing inward, curving under the influence of the Sun, and moving fast enough to continue out the other side. The Sun can alter its direction and warm the ice on its surface, but it cannot keep the object forever. This is where the idea of an open orbit becomes important. We do not need equations to understand the central meaning. A closed orbit is like a journey that eventually returns, no matter how long it takes. An open orbit is more like a single visit. The object enters the sun's region of influence. Its path bends under gravity, but it is not compelled to come back. For astronomers, this is not a feeling or an impression. It is the result of measuring the object's position over time, calculating its speed and direction, and comparing that path with what the sun's gravity is capable of holding. When the trajectory does not close, and when the object's speed and orbital shape show that it carries enough energy to leave, an enormous conclusion can be drawn from a tiny point of light. It was not born here, or at the very least, it no longer belongs to this system. What is striking is that this discovery does not make the sky any louder. From the ground, 3i, Atlas remains far too faint for ordinary human perception. It does not change our night, alter the tides, or pull the planets away from their familiar paths. All it does is pass quietly through, while instruments built by human hands begin to recognize the difference in its motion. Its strangeness does not lie in its appearance, but in its path. And in astronomy, a path can sometimes tell us more than a shape ever could. Objects within the solar system usually carry a shared history. They formed from the material left around the young sun, endured early collisions, were pulled and rearranged by the giant planets, and still bear the marks of this home's formation billions of years later. When a familiar comet travels inward, we can think of it as a preserved fragment from the solar system's youth. But with 3i, Atlas, its path opens another possibility. Its material may not be an old page from the sun's own book, but a page blown here from another one. It may have formed around a distant star, been thrown from its home by the gravity of a large planet, and then traveled through interstellar darkness for so long that its original birthplace has nearly vanished from view. Science, however, does not rush to turn an unusual trajectory into a complete story. Identifying the object as interstellar is only the first step. It shows that the sun does not hold it in a familiar orbit, but it cannot yet tell us which star it came from, how long it has been traveling, or what environments it passed through before arriving here. Its path is like an address that has been almost completely erased, leaving behind only one clear sign. Its origin lies beyond the solar system. To understand more, astronomers need other kinds of data: the sunlight reflected from its surface, the gases released as it warms, the chemical composition of its thin coma, and the microscopic ratios preserved within its molecules. So the opening of this story is not a complete answer, but the moment a door begins to open, a faint point of light is detected. Separate positions are connected. An orbit gradually comes into focus, and that orbit reveals that this is not a distant member returning home, but an object passing through the solar system from the space beyond it. From a nearly unremarkable speck, the presence of a rare visitor in the galaxy is recognized, a fragment of matter that does not belong to the sun's gravitational family. Once it became clear that the object did not follow the familiar behavior of comets bound to the solar system, another question naturally emerged. If its path shows that 3i, Atlas, came from somewhere else, what does the symbol 3i in its name actually mean? And why is that small designation enough to place it among such a rare group of objects? In astronomy, names are rarely created to evoke emotion. They are not chosen in the same way people name a landscape, a river, or a story. Most of the time, the name of an object in space is built as a system of record keeping, with each symbol serving a specific purpose: the time of discovery, the survey that found it, and, most importantly, its place within the way humans classify the things drifting among the stars. At first glance, 3i Atlas may look like nothing more than a short string of characters. But in the language of science, it is a marker showing that this object lies beyond the familiar boundaries of the solar system. The word Atlas at the end is not the part carrying the deepest cosmic meaning. It is the signature of the observing system that discovered the object. ATLAS is a network of telescopes designed to scan the sky, not primarily to search for distant mysteries in interstellar space, but to detect objects that might approach Earth, subtle changes in the motion of points of light, and signs that could easily be missed by the unaided eye. Among the immense volume of data the system produces each night, a faint point like 3i, ATLAS is only one signal among millions, until its motion begins to depart from what astronomers expect. The part that truly changes the meaning of the name comes first, the number and the letter, 3i. In this naming system, the I is not an arbitrary symbol. It stands for interstellar. This is how scientists classify objects that did not form within the solar system, but instead arrived from the space between other star systems. They do not orbit the sun like planets, they are not held within long paths like traditional comets, and they do not belong to any population that formed alongside Earth. They are travelers passing through, appearing only briefly, long enough to be recorded before continuing on their way. The number before the I tells us where the object stands in the history of observation. 3I means that it is the third confirmed interstellar object ever observed passing through the solar system. Before it, humanity encountered two similar visitors, Oumuamua, which appeared in 2017, and 2I, Borisov, discovered in 2019. Each time, the astronomical community has had to adjust part of its understanding of the space surrounding the solar system, because these objects are not only rare, but also carry information that ordinary simulations cannot reproduce. They offer direct evidence that matter does not move only within individual star systems, but can also be exchanged between them over the immense timescales of the galaxy. Yet the most important point is not how many such objects have been found. It is that every discovery forces us to reconsider something that once seemed settled, the boundary of the solar system. In the popular imagination, the solar system is often pictured as a region with a clear edge, where the planets end and empty space begins. In reality, that boundary is not a wall. It is a transition zone, where the sun's gravitational influence gradually weakens without disappearing entirely, and where objects from outside can still enter, interact, and leave again if they are moving fast enough. Interstellar objects, such as 3I, Atlas, are vivid evidence of how open this region truly is. When an object carries the label interstellar, it tells us more than simply that it came from outside. It also shows that other star systems are capable of creating, holding, and eventually losing some of their own material. A comet like 3I, Atlas, may once have formed within a disk of matter around a distant star, passed through the chaotic early stages of that planetary system, and then been thrown from its home by a powerful gravitational force, perhaps from a giant gas planet or a close stellar encounter. From there, it would have begun a long journey through the space between the stars, a journey with no destination, only occasional passages through other star systems. What makes the designation 3I so remarkable is that it is not merely another number on a list. It is a sign that humanity has begun to recognize an entirely different class of object from those described in astronomy for many decades. In the past, comets were always understood as members of the solar system, no matter how long their orbits might be. But the arrival of interstellar objects has opened a new category, one in which some comets do not belong to any star system we are directly observing, yet still pass through our own as temporary visitors. From the perspective of orbital physics, this distinction is not a minor detail. A comet belonging to the solar system always carries the imprint of the sun's gravity as a fundamental bond. No matter how far it travels, its motion can still be described as part of a closed system. An interstellar object, by contrast, carries enough energy to avoid being bound to the sun over the long term. It arrives from outside, its path is bent as it passes through, and then it continues outward along a trajectory that never closes. That slight difference in orbital energy is enough to separate two worlds that may otherwise appear nearly identical. One is a member of the Sun's family, while the other is simply passing by. In the case of 3I, Atlas, this became even clearer when early observations showed that its orbit did not fit any long-term cometary model within the solar system. It was not simply an object from the distant outer regions being drawn inward. It followed an open trajectory, meaning that after passing through the region near the Sun, it would continue outward rather than return. Because of this, the designation 3I is more than a technical label. It is a confirmation that we are observing an object that belongs to the space between star systems. Even so, the deeper meaning of the name is not found only in classification. It also lies in the way it changes our sense of where we are in the universe. When an object is labeled interstellar, it reminds us that the solar system is not isolated. It is part of a much larger network, where matter can travel from one place to another across spans of time longer than the entire history of Earth. What we call out there is not completely separate from us. Sometimes, it can pass surprisingly close, near enough to be observed, measured, and used to deepen our understanding of origins, including our own. As the layers of meaning within the name begin to unfold, the story is no longer only about a scientific designation. It leads toward a broader question about the nature of the object itself. If 3I Atlas truly came from another star system, what chemical traces has it carried with it, and what might its light reveal about the place where it was born? After the orbit of 3I, Atlas was confirmed to be an open path. No longer bound to the Sun over the long term, scientific attention gradually shifted from the question of where it came from to a deeper layer of information, one in which the object could be understood not by its position, but by the way it responded to the light of the star it was passing. At a great distance, a comet is almost indistinguishable from the darkness around it. It exists as a frozen mass of ice and dust, held in a stable state for billions of years, where temperatures are so low that volatile molecules have almost no opportunity to escape. In that condition, the comet is like a sealed storehouse of material, preserving the environment in which it originally formed without being greatly disturbed by time. But as it moves gradually into the Sun's region of influence, that state begins to change, not through a sudden event, but through a slow and continuous process. Light and heat from the Sun do not immediately break apart the comet's structure. Instead, they gradually penetrate its surface layers, causing the weaker bonds within the ice to become unstable. In the near vacuum of space, rather than melting into liquid, the molecules pass directly from solid into gas, through a process of sublimation that unfolds silently but without pause. From this process, a region of material begins to form around the nucleus. Known as the coma, this region is not a fixed shell, but a temporary space in which matter is continually released and spreads outward. It gradually expands, pushed by radiation pressure and the solar wind, forming a soft, faint, and constantly changing structure. From a distance, the coma may look like a very thin mist surrounding a dark point, but in reality, it is the place where the comet is breathing out its internal material into space. What matters is that the substances released during this process are not newly formed. They are molecules that have existed within the comet's structure for an immense span of time, preserved since the object formed in the disk of material surrounding a star. Water, carbon dioxide, carbon monoxide, and many other volatile compounds appear not because new reactions are creating them, but because they are escaping from where they had long been locked within the ice. For 3I, Atlas, this process carries a deeper significance. This is not a comet already familiar with the environment of the solar system, but an object carrying a history of formation from another star system. As its ice begins to sublimate, molecules bearing traces of that primordial environment gradually emerge into the gas surrounding it, creating a rare opportunity to observe interstellar material in a state as close to its original form as possible. From Earth, no one can reach out and touch this comet, and there is no need to send a spacecraft to collect a sample directly. Instead, light becomes the only intermediary. As sunlight, or light from the background of space, passes through the comet's thin coma, it interacts with the molecules present there. Some of that light is absorbed at specific wavelengths, creating tiny gaps within the electromagnetic spectrum. These gaps are not random absences, but distinctive signatures of particular molecules. Every molecule interacts with light in its own way, like a unique signature that cannot easily be mistaken for another. When telescopes analyze the light received from 3I, Atlas, they are not merely measuring its brightness or shape. They are reading an invisible structure encoded within its spectrum. In this way, water, carbon dioxide, and other volatile compounds can gradually be identified, not through direct images, but through the changes they produce in the light passing through them. During this process, the comet is no longer simply a physical object. It becomes a system that reveals information about itself through its interaction with light. There is no language and no deliberate signal, yet its internal structure is reflected indirectly through extremely subtle changes in the electromagnetic spectrum. This is why a comet can be understood as a kind of natural record, preserving the conditions of its formation and revealing them only when it enters an environment close enough to awaken its frozen material. At the level of observation, all of this happens in complete silence. There is no sudden change in the sky and no event visible to the unaided eye, only light data recorded by sensitive instruments. Yet within that data, a picture is gradually taking shape, a picture of the object's chemical structure that speaks not only of its present condition, but also of the distant environment that existed when it was first formed. To read this picture correctly, however, scientists must separate what is primordial from what has been altered during the object's long journey. As it traveled through interstellar space and later approached the Sun, the comet's surface may have been affected by radiation, collisions with dust grains, or uneven heating. These processes may have changed part of its outer structure, while deeper layers remained more faithful to their original state. For this reason, studying 3I Atlas involves more than simply recording what is appearing now. It is also a process of separating layers of information, trying to understand which features formed in the distant past and which were created or transformed during the more recent stages of its journey. Each measurement of light becomes a small cross-section of history, incomplete, but still capable of offering glimpses into an environment entirely different from the solar system. Throughout this quiet process, the comet continues moving through the Sun's region of influence. It does not alter the orbits of the planets or create any noticeable effect on the space surrounding Earth. Yet, during the brief period in which its ice is being warmed, it becomes one of the rare sources of material that allows humanity to observe directly the composition of an object from beyond the solar system. And as light continues to pass through that thin cloud of gas, carrying subtle distortions filled with information, the story of 3I Atlas begins to open into a deeper realm, where chemical traces speak not only about the object itself, but also about the vast environment that created it long before it entered the light of the Sunday. At a distance of millions of kilometers, 3I Atlas is no longer an image that can be observed directly in the ordinary sense. Instead, it exists only as a point that influences the stream of light passing through its region of space, an effect so subtle that it can be recorded only by some of the most sophisticated observing instruments humanity possesses. In this case, light is no longer simply what allows us to see an object. It becomes a stream of information that has passed through several different environments, beginning at the Sun, spreading outward through space, then traveling through the thin cloud of gas surrounding the comet before continuing toward telescopes on Earth. Throughout that journey, the light is neither lost nor destroyed, but its structure is continually altered in ways far too subtle for the human eye to detect. We can imagine light as a continuous current and the gas around the comet as an extremely diffuse region through which that current must flow. As it passes through, certain portions of the light are weakened, while others remain almost unchanged, producing a very slight distortion in the original pattern. This distortion has no visible shape of its own, but it remains as a kind of trace that begins to emerge only when the light is separated into its individual wavelengths. Once the light is divided in this way, it no longer appears as a perfectly continuous band. Instead, it reveals a structure containing areas of reduced intensity at very specific positions. These missing regions are not random gaps. They mark the wavelengths at which light has been absorbed by molecules within the gas surrounding the comet. Each type of molecule interacts with light in its own distinctive way, absorbing only certain amounts of energy and creating characteristic marks within the observed spectrum. When studied carefully enough, this structure begins to look less like a physical graph and more like a pattern with a rhythm of its own. Some regions are noticeably weakened, while others remain almost untouched, and the entire distribution reflects the chemical substances present within the coma. Among them are water, carbon dioxide, carbon monoxide, and many other volatile compounds, all of which had been held within the comet's icy nucleus long before it approached the Sunday. As that ice begins to receive energy from sunlight, its original balance is gradually disturbed. This does not happen through a sudden collapse, but through a continuous process of release, as molecules slowly escape from the surface and form a cloud of gas around the nucleus. That gas becomes the intermediate medium through which light passes and is altered, creating the data that telescopes are able to collect. In the case of 3I, Atlas, this layer of information carries an additional depth. The object did not form within the environment of the solar system, so the molecules being observed may reflect more than its present response to the Sunday. They may also preserve traces of an entirely different environment, where temperatures, radiation, and chemical conditions were unlike those found anywhere near our star. None of these processes unfolds in a way that can be seen directly. From the perspective of the night sky, 3I, Atlas remains only a faint object moving through a familiar region of space. But at the level of data, the light that has passed through it is continually changing in structure, like a stream of information being edited by the material it encounters. There are moments during observation when the entire phenomenon seems almost motionless. The comet continues along its path, the coma expands very slowly, and the light continues to be altered as it travels through. There is no distinct event and no sudden burst, only the accumulation of extremely small changes in the spectrum, gradually forming a more complete picture of the object. Within that growing picture, the comet is no longer understood only as a mass of ice passing through the solar system. It becomes a temporary region of interaction between matter and light, where information about its internal structure is revealed indirectly. Without touching it or approaching it, humanity can still detect traces of the conditions that created it long before it entered the range of Earth's observations. And as light continues to pass through that cloud of material, carrying changes that are subtle yet consistent, 3I, Atlas gradually becomes a rare example of how the universe can reveal its own structure through invisible interactions between light and ancient ice. Among the data returned by the James Webb Space Telescope during its observations of 3I, Atlas, one detail may seem small at first, yet it cannot be overlooked from the perspective of astrochemistry. The presence of deuterium, also known as heavy hydrogen, at an unusually high abundance compared with comets previously observed within the solar system. This did not appear as an obvious signal from the beginning. In the first spectra, deuterium left only extremely subtle variations, scattered across the absorption regions associated with water and certain hydrogen-bearing compounds. Only when the full set of data was placed side by side and compared across multiple wavelength bands and different observation periods did a new pattern begin to emerge, one in which the ratio between ordinary hydrogen and deuterium no longer fell within the familiar range. To understand why this matters, we need to return to the physical nature of deuterium itself. It is not an entirely different element, but an isotope of hydrogen. Its nucleus contains the familiar proton, along with one additional neutron. This very small difference does not fundamentally change the way it participates in the chemical structure of water, but it does alter certain physical properties, especially its mass and the way it behaves in low-temperature environments. In the depths of space, where temperatures can fall close to absolute zero, differences this small are not simply erased over time. Instead, they tend to be preserved within the icy structures of small objects, such as comets. When water forms under deeply cold conditions, the ratio of hydrogen to deuterium within it can directly reflect the environment in which that ice was created. A colder, more stable region that remains undisturbed for a long period may allow deuterium to accumulate at higher levels than in warmer areas, or in places more heavily altered by radiation. For this reason, when scientists study a comet, especially an object like 3I Atlas, its deuterium ratio is not treated as an isolated number. It is more like an indirect indicator of the environment in which the object originally formed. It does not describe the comet's present surroundings or its recent journey, but rather the state of space at the time when its earliest ice first came into being. In the James Webb data, this ratio appeared to be more than slightly elevated compared with comets in the solar system. The difference was large enough to attract the attention of the observing community. Some early estimates suggested that the deuterium abundance could be about 30 times higher than values previously measured in familiar comets. If confirmed through further independent observations, such a result would reveal a substantial difference between the environment where 3I Atlas formed and the conditions that shaped objects in the Sun's neighborhood. In observational science, however, a number like this is never treated as an absolute conclusion. Deuterium is not a precise clock. It does not directly tell us when an object was created. Instead, it reflects the conditions of the place where that object formed, and those conditions could arise in several different settings. A cold region of a gas disk, far from the center of a star system, a very early stage in the history of planetary formation, or an area of the Milky Way where matter had undergone less reprocessing by earlier generations of stars. This makes the interpretation far more complex than a simple measurement. Rather than searching for one exact point in time, scientists must place the deuterium ratio within a wider network of evidence, including the presence of water, carbon monoxide, carbon dioxide, and many other volatile compounds. Only by examining the relationships among all these components can the picture of the object's formation environment begin to take on meaning. In the case of 3I Atlas, early observations suggested that deuterium was not the only feature that differed. The overall structure of its volatile molecules also did not perfectly match what had previously been recorded in the solar system. Some ratios between water and carbon-bearing compounds appeared slightly shifted, not enough to create a complete separation, but enough to suggest that the chemistry of its birthplace may have followed a different path. These differences are not viewed as signs of an isolated exception. Instead, they are placed within the much broader context of the galaxy. The Milky Way is not a uniform environment. It contains countless star-forming regions with widely varying temperatures, densities, and radiation conditions. Each of these regions may leave its own chemical signature within small bodies, such as comets and 3I. Atlas may simply be one of the rare examples that allows humanity to examine such a signature directly. As the ice on its surface continues to sublimate, while it moves closer to the Sun, deuterium-bearing molecules are also released into the coma, where they take part in the same interactions with light as the other compounds. From such a great distance, there is no way to distinguish every individual molecule directly in real time. What telescopes can observe is the overall change in the spectrum, where the signatures of deuterium contribute to the larger structure of the signal. Throughout this process, there is no perfectly clear boundary between what is original and what belongs to the present. Every observation contains several overlapping layers of information. The deepest layer reflects the conditions of formation. The middle layer records the object's long journey through interstellar space, and the surface layer reveals its recent interaction with the sunday. Deuterium is only one of these layers, but it is sensitive enough to reveal subtle differences between cosmic environments. Seen from a wider perspective, signals like these tell us more than the story of a single object. They offer a glimpse into the way matter is distributed throughout the galaxy, where each star system may leave its own chemical trace within tiny fragments cast out into interstellar space. In this sense, 3I, Atlas is not merely a comet passing through the solar system. It is a piece of matter carrying part of the chemical structure of a distant environment, crossing into humanity's field of observation during one very brief moment in cosmic history. The traces of deuterium in the gas surrounding 3I, Atlas draw attention away from the sun's present region of light and toward a place that can no longer be located on any map of the galaxy. There, long before this object entered the solar system, its earliest molecules may have settled onto cold grains of dust, gradually becoming part of a small body of ice forming around a distant star. That birthplace has not been found, but the chemistry that remains allows us to imagine something of the environment that once surrounded it. Faint light, low temperatures, and processes unfolding so slowly that even the smallest differences between atoms had time to accumulate. A planetary system begins as a vast and unsettled structure. Around a young star lies a disk of gas, dust, and icy particles moving along orbits that have not yet become entirely stable. The region close to the star receives more heat, making it difficult for water and many other volatile substances to remain frozen. Farther out, temperatures fall, allowing molecules to settle onto the surfaces of dust grains and remain there for longer periods. Each distance within the disk is like a climate zone of its own, quietly determining which kinds of material can survive there. Comets usually form within the colder regions of this disk. They do not appear immediately as large bodies of ice, but begin with grains of dust so small that the human eye could never see them. Water and many other compounds collect in extremely thin layers around those grains. Through countless gentle collisions, the particles begin to stick together, forming larger clusters that continue gathering more material. Tiny grains of ice become pebbles, pebbles combine into larger bodies, and over a long enough span of time, an object may grow large enough to exist as a comet in its own right. Throughout this process, the chemistry of the ice is not arranged at random. Temperature, gas density, radiation levels, and distance from the star all influence how molecules form. Some substances can freeze only in exceptionally cold regions, while others can survive somewhat closer to the star. Even within the same molecule of water, the ratio between ordinary hydrogen and deuterium can vary depending on the surrounding conditions. Once the ice is buried beneath new layers of material, those ratios may remain preserved as part of the object's internal structure. Cold plays an important role not because it causes time to stop, but because it slows the processes that might rewrite the original chemistry. In a region that is repeatedly heated, ice may evaporate, condense again, break apart, and then reform. Each cycle of change can blur the older record. Farther from the star, where less energy is available and variations unfold more slowly, material may avoid repeated reprocessing. Molecules created during the earliest stages can remain quiet within the ice, covered by newer layers and gradually becoming part of the object's deeper interior. This is why comets are sometimes described as archives of young planetary systems, although the comparison should not be taken too far. No body of ice is ever completely isolated from its environment. While it still remained around its parent star, 3I, Atlas may have traveled through regions of different temperatures, endured collisions, or been altered by radiation. After it was expelled into interstellar space, its surface continued to encounter high-energy particles and microscopic impacts with extremely diffused dust. Its outermost layers may have changed substantially, while the deeper material remained better protected. What Webb observes today is not a perfectly preserved record of the day the comet was born. The data is more like an old page that still contains a few readable lines, while other sections have faded or been written over. The work of scientists is to distinguish which traces may belong to the formation environment and which appeared during the object's long wandering between the stars or after the sun began to warm it. That caution is especially important when connecting a cold formation environment with the age of 3I, Atlas. A high deuterium ratio suggests that the ice may have formed under extremely cold conditions, but the ratio itself does not function like a clock with a date already written upon it. A younger star system could still contain regions cold enough to produce a similar value. In the same way, a very ancient object that had been heated and reprocessed many times might no longer preserve a clear sign of its original state. The comet's age can only be inferred when isotopic data is placed alongside many other chemical components and compared with models of the Milky Way's chemical history. Although it cannot yet provide a certain date, the difference between 3I, Atlas, and comets in the Solar System remains deeply significant. The comets surrounding the Sun are not all alike. Some come from the Kuiper belt, while others arrive from the Oort cloud, and their chemical compositions reflect different regions of formation within the early solar disk. Even so, the signature measured by Webb in this interstellar visitor appears to lie well beyond the range normally encountered, suggesting that its material was shaped in an environment unlike our own. That difference does not necessarily require an entirely unfamiliar kind of matter. The galaxy uses the same basic elements to create stars, planets, and comets: hydrogen, oxygen, carbon, nitrogen, and many heavier elements. What makes each environment distinctive is the proportion of those elements and the ways in which they combine. Water still has its familiar structure, but the amount of deuterium preserved within it may differ. Carbon dioxide remains a common molecule, but its abundance relative to water can reflect a different thermal history. Only a few small variations may be enough to show that the object did not form under the same conditions as the comets surrounding the Sunday. Each planetary system can be imagined as a geographical region with its own chemical climate. Two places may both contain rock, water, and air, yet differences in their proportions, temperatures, and histories of change can create very different landscapes. A comet expelled from its parent system carries part of that landscape with it in the form of ice and dust. When it passes close to another star, its ice begins to vaporize, allowing ratios established in a distant place to appear once again within the light. For 3I, Atlas, the cold environment may have existed within the molecular cloud even before its parent star formed. Clouds like these contain gas and dust at extremely low temperatures, cold enough for water and many other molecules to accumulate on the surfaces of dust grains. When part of the cloud collapsed to create a star and the disk surrounding it, that ancient ice may have been carried along, mixed with newer material, and eventually incorporated into growing comets. In this possibility, some of the comet's chemistry could be older than the star that gave birth to its planetary system. Another, simpler possibility is that the object formed in a very distant region of the disk around its star, where the young star's light had grown faint and temperatures remained low for an extended period. There, deuterium may have continued to become enriched within the ice before the material gathered into a comet. These two settings could leave behind similar signatures, making it impossible for the present data to determine exactly which stage played the greater role. What Webb provides is not a precise address for the object's birthplace, but a set of limits on the kind of environment that must once have existed. Those limits are already immensely valuable because the solar system is the only planetary system humanity can study from within. Every cometary sample approached by a spacecraft, every grain of dust collected, and every isotopic ratio measured directly belongs to the same shared history surrounding the Sunday. 3I, Atlas offers a point of comparison from outside. It does not allow us to see an entire distant star system, but it carries a fragment small enough to pass quietly through our own, yet rich enough to demonstrate that disks around other stars can create material bearing significantly different signatures. The number of confirmed interstellar objects is still far too small to tell whether 3I Atlas represents a common population or an unusual case. Smaller, darker objects, or those passing through along paths that are difficult to observe, may have crossed the solar system without ever being detected. The data we have today is like a few grains of sand collected from an immense shoreline, not nearly enough to describe the entire landscape. Even so, a single grain with an unusual composition is enough to show that the distant shore is not entirely like the ground beneath our feet. As 3I Atlas continues to be warmed by the sun, molecules trapped within its ice escape, little by little, blending into the coma before spreading outward into space. Some are broken apart by sunlight, while others absorb or emit radiation at wavelengths Webb can detect. This period of observation occupies only a tiny fraction of the comet's lifetime, yet it opens a narrow window onto the environment that created it. The sun did not write those chemical signatures. Its light merely allows an ancient record to become visible. The birthplace of 3I Atlas may have changed long ago. The original disk of gas and dust almost certainly no longer exists in its earlier form. Planets may have formed, shifted their orbits, or collided with one another. The parent star may still be shining somewhere in the galaxy, but the connection between it and the fragment of ice that was cast away is now almost impossible to reconstruct. What remains is the chemistry preserved within the comet, durable enough to cross interstellar space and appear in the data of a telescope belonging to an entirely different planetary system. Within a small amount of ice, evaporating beneath the sun's light, Webb has glimpsed the outline of an unfamiliar birthplace. The cold that once surrounded that place is no longer present, but the ratios shaped within it have endured, ready to lead the story toward an even more distant age, when the sun itself had not yet begun to shine. The traces of deuterium in the gas surrounding 3I Atlas draw our attention away from the sun's present region of light and toward a place that can no longer be identified on any map of the galaxy. There, long before this object entered the solar system, its earliest molecules may have settled onto cold grains of dust, gradually becoming part of a small body of ice forming around a distant star. That birthplace has not been found, but the chemistry that remains allows us to imagine something of the environment that once surrounded it. Faint light, low temperatures, and processes unfolding so slowly that even the smallest differences between atoms had time to accumulate. A planetary system begins as a vast and unsettled structure. Around a young star lies a disk of gas, dust, and icy particles moving in orbits that have not yet become entirely stable. The region close to the star receives more heat, making it difficult for water and many other volatile substances to remain frozen. Farther out, temperatures fall, allowing molecules to settle onto the surfaces of dust grains and remain there for longer periods. Each distance within the disk is like a climate zone of its own, quietly determining which kinds of material can survive there. Comets usually form within the colder regions of this disk. They do not appear immediately as large bodies of ice, but begin with grains of dust so small that the human eye could never see them. Water and many other compounds collect in extremely thin layers around those grains. Through countless gentle collisions, the particles begin to stick together, forming larger clusters that continue gathering more material. Tiny grains of ice become pebbles, the pebbles combine into larger bodies, and over a long enough span of time, an object may grow large enough to exist as a comet in its own right. Throughout this process, the chemistry of the ice is not arranged at random. Temperature, gas density, radiation levels, and distance from the star all influence how molecules form. Some substances can freeze only in exceptionally cold regions, while others can survive somewhat closer to the star. Even within the same molecule of water, the ratio between ordinary hydrogen and deuterium can vary depending on the surrounding conditions. Once the ice is buried beneath new layers of material, those ratios may remain preserved as part of the object's internal structure. Cold plays an important role not because it causes time to stop, but because it slows the processes that might rewrite the original chemistry. In a region that is repeatedly heated, ice may evaporate, condense again, break apart, and then reform. Each cycle of change can blur the older record. Farther from the star, where less energy is available and variations unfold more slowly, material may avoid repeated reprocessing. Molecules created during the earliest stages can remain undisturbed within the ice, covered by newer layers and gradually becoming part of the object's deeper interior. This is why comets are sometimes described as archives of young planetary systems, although the comparison should not be taken too far. No body of ice is ever completely isolated from its environment. While it still remained around its parent star, 3I, Atlas may have traveled through regions of different temperatures, endured collisions, or been altered by radiation. After it was expelled into interstellar space, its surface continued to encounter high-energy particles and microscopic impacts with extremely diffuse dust. Its outermost layers may have changed substantially, while the deeper material remained better protected. What Webb observes today is not a perfectly preserved record of the day the comet was born. The data is more like an old page that still contains a few readable lines, while other sections have faded or been written over. The work of scientists is to distinguish which traces may belong to the formation environment and which appeared during the object's long wandering between the stars or after the sun began to warm it. That caution is especially important when connecting a cold formation environment with the age of 3I Atlas. A high deuterium ratio suggests that the ice may have formed under extremely cold conditions, but the ratio itself does not function like a clock with a date already written upon it. A younger star system could still contain regions cold enough to produce a similar value. In the same way, a very ancient object that had been heated and reprocessed many times might no longer preserve a clear sign of its original state. The comet's age can only be inferred when isotopic data is placed alongside many other chemical components and compared with models of the Milky Way's chemical history. Although it cannot yet provide a certain date, the difference between 3I, Atlas, and comets in the solar system remains deeply significant. The comets surrounding the Sun are not all alike. Some come from the Kuiper belt, while others arrive from the Oort cloud, and their chemical compositions reflect different regions of formation within the early solar disk. Even so, the signature measured by Webb in this interstellar visitor appears to lie well beyond the range normally encountered, suggesting that its material was shaped in an environment unlike our own. That difference does not necessarily require an entirely unfamiliar kind of matter. The galaxy uses the same basic elements to create stars, planets, and comets: hydrogen, oxygen, carbon, nitrogen, and many heavier elements. What makes each environment distinctive is the proportion of those elements and the ways in which they combine. Water still has its familiar structure, but the amount of deuterium preserved within it may differ. Carbon dioxide remains a common molecule, but its abundance relative to water can reflect a different thermal history. Only a few small variations may be enough to show that the object did not form under the same conditions as the comets surrounding the Sunday. Each planetary system can be imagined as a geographical region with its own chemical climate. Two regions may both contain rock, water, and air, yet differences in their proportions, temperatures, and histories of change can produce very different landscapes. A comet expelled from its parent system carries part of that landscape with it in the form of ice and dust. When it passes close to another star, its ice begins to vaporize, allowing ratios shaped in a distant place to appear once again within the light. For 3I, Atlas, the cold environment may have existed within the molecular cloud even before its parent star formed. Clouds like these contain gas and dust at extremely low temperatures, cold enough for water and many other molecules to accumulate on the surfaces of dust grains. When part of the cloud collapsed to create a star and the disk surrounding it, that ancient ice may have been carried along, mixed with newer material, and eventually incorporated into growing comets. In this scenario, some of the comet's chemistry could be older than the star that gave birth to its planetary system. Another, simpler possibility is that the object formed in a very distant region of the disk around its star, where the young star's light had grown faint and temperatures remained low for a long time. There, deuterium may have continued to become enriched within the ice before the material gathered into a comet. These two environments could leave behind similar signatures, so the available data cannot yet determine exactly which stage played the greater role. What Webb provides is not a precise address for the object's birthplace, but a set of limits on the kind of environment that must once have existed. Those limits are already immensely valuable, because the solar system is the only planetary system humanity can study from within. Every cometary sample approached by a spacecraft, every grain of dust collected, and every isotopic ratio measured directly belongs to the same shared history surrounding the Sunday. 3i. Atlas offers a point of comparison from outside. It does not allow us to see an entire distant star system, but it carries a small fragment enough to demonstrate that disks around other stars can create material with significantly different signatures. The number of confirmed interstellar objects is still far too small to tell whether 3i Atlas represents a common population or an unusual case. Smaller, darker objects, or those passing through along paths that are difficult to observe, may have crossed the solar system without ever being detected. The data we have today is like a few grains of sand collected from an immense shoreline, not nearly enough to describe the entire landscape. Even so, a single grain with an unusual composition is enough to show that the distant shore is not entirely like the ground beneath our feet. As 3i Atlas continues to be warmed by the sun, molecules trapped within its ice escape little by little, blending into the coma before spreading outward into space. Some are broken apart by sunlight, while others absorb or emit radiation at wavelengths Webb can detect. This period of observation occupies only a tiny fraction of the comet's lifetime, yet it opens a narrow window onto the environment that created it. The sun did not write those chemical signatures. Its light merely allows an ancient record to become visible. The birthplace of 3i Atlas may have changed long ago. The original disk of gas and dust almost certainly no longer exists in its earlier form. Planets may have formed, shifted their orbits, or collided with one another. The parent star may still be shining somewhere in the galaxy, but the connection between it and the fragment of ice that was cast away is now almost impossible to reconstruct. What remains is the chemistry preserved within the comet, durable enough to cross interstellar space and appear in the data of a telescope belonging to an entirely different planetary system. Within a small amount of ice evaporating beneath the sun's light, Webb has glimpsed the outline of an unfamiliar birthplace. The cold that once surrounded that place is no longer present, but the ratios shaped within it have endured, ready to lead the story toward an even more distant age, when the sun itself had not yet begun to shine. The sun often feels like an almost permanent presence. It was shining before humans appeared, before the first forests, and even before most of the complex history of life on Earth. Daylight is so familiar that it is difficult to imagine our star once having a beginning, or that before it was born, the Milky Way had already passed through a span of history longer than the entire present age of the solar system. The sun's 4.5 billion years are almost beyond comprehension on the scale of a human life, but on the timeline of the galaxy, they do not belong to the opening chapter. Many generations of stars had already flared into existence and faded away, leaving behind gas, dust, and newly created elements for the generations that followed. 3i Atlas is passing through our region of space, carrying traces that seem to belong to that earlier history. Its high deuterium ratio suggests that its ice may have formed in an environment of profound cold, where it remained largely untouched by prolonged heating. Yet cold describes only one part of its birthplace. To place the object within the broader timeline of the Milky Way, scientists also look to carbon, an element present in many of the molecules Webb detected around the comet. Carbon tells us more than what the object contains. Its isotopes can also reflect how extensively the material within a star system had been enriched by earlier generations of stars. Most familiar carbon is carbon 1,2 with 6 protons and 6 neutrons in its nucleus. Carbon 1,3 contains 1 additional neutron. It is less common, but still occurs naturally in gas, rock, living organisms, and the clouds between the stars. These two isotopes participate in nearly the same chemical reactions, but the ratio between them has not remained exactly the same throughout the history of the galaxy. As generations of stars are born, exhaust their fuel, and return material to space, they gradually alter the composition of the interstellar environment. Over many cycles, certain rare isotopes, including carbon 1,3, become increasingly abundant in the clouds of gas that will eventually form new star systems. The Milky Way can be imagined as a landscape built up over countless seasons. The earliest stars formed from relatively simple material, composed mainly of hydrogen and helium, along with small amounts of heavier elements produced by the earliest stellar generations. Within stellar cores, nuclear reactions gradually created carbon, oxygen, and many other elements. When stars shed their outer layers or ended their lives in powerful events, this transformed material returned to space, mixed into clouds of gas, and became part of the next generation of stars. Each new generation did not begin with exactly the same mixture as the one before it, but inherited more of what older stars had left behind. The Sun was born relatively late in this long process of enrichment. The cloud that formed the Solar System already contained many heavy elements, and rare isotopes accumulated over billions of years of galactic evolution. The iron in Earth's core, the calcium in rocks and bones, the oxygen in the oceans, and the carbon in every living thing all became part of this home because of generations of stars that existed before the Sunday. The Solar System was not created from the pristine matter of the early universe, but from a mixture that had been recycled and enriched throughout the long history of the galaxy. Near-spec data indicates that 3I, Atlas contains only a small amount of carbon, 1,3 relative to carbon, 1,2, lower than the familiar level found in material around the Sunday. That relative scarcity is consistent with an earlier formation environment, when the Milky Way had not yet passed through enough generations of stars to add as much carbon, 1,3, to its clouds of gas. This is a different kind of clue from deuterium. The heavy hydrogen ratio points toward the temperature and heating history of the ice, while the carbon ratio places that material within the chemical evolution of the galaxy. The two signals do not tell exactly the same story, but both lean toward an origin more distant and more ancient than the Solar System. Together, these clues make 3I, Atlas, especially remarkable. A cold environment can exist at many points in time, even around a relatively young star, so deuterium alone is not enough to determine age. The unusual carbon ratio provides an independent clue, suggesting that the parent system may have formed when the Milky Way had been less enriched by previous generations of stars. When these two layers of data are considered together, the emerging picture is no longer simply one of a region far from a star, but potentially of a planetary system belonging to a much earlier stage in the history of the galaxy. Using models that combine carbon composition with deuterium abundance, the research team estimates that the material within 3I, Atlas, may have formed roughly 10 to 12 billion years ago. This should not be treated as a directly measured birth date. There is no clock hidden inside the comet, and no single observation can determine its age with precision down to a particular billion-year interval. Instead, this estimated range is inferred from the agreement between the chemical data and models describing how the Milky Way has changed over time. New observations or improved modeling could still revise that estimate. Even within those cautious limits, the possibility opens onto an extraordinary depth of time. If 3I Atlas truly formed 10 to 12 billion years ago, it came into existence when the universe was far younger than it is today. The sun did not yet exist. The cloud that would eventually create the solar system had not taken on any familiar form, and many of the elements surrounding us had not yet been distributed in the proportions we know today. The Milky Way was actively forming stars, continually turning gas into new points of light and allowing its earliest stellar generations to begin enriching the environment around them. Astronomers refer to part of this era as cosmic noon, not because the universe shares a single sun, but because the rate of star formation reached an exceptionally high level. Many galaxies were creating stars more rapidly than they do today. Dense clouds of gas were continually collapsing, while the light of young stars filled the growing regions of the universe. This is very different from the stillness we often associate with deep space. On a galactic scale, it was a period when many structures were being built, many elements were being created, and countless early planetary systems may have begun forming around newborn stars. Somewhere within that setting, a cold cloud of gas may have collapsed, giving birth to a star and the disk of material surrounding it. Deep regions of the cloud, shielded from many sources of heat, may have allowed ice-coated dust grains to remain cold for long periods. Tiny fragments gradually gathered together. Some became the seeds of planets, while others remained in the outer regions and formed comet-like bodies. 3I Atlas may once have been one of those fragments, unremarkable among billions of other icy bodies, carrying only the chemical composition of the age in which it was made. The original star system did not necessarily remain peaceful. During its early stages, large planets may have migrated, exchanged momentum with smaller bodies, and reshaped the structure of the entire system. A close encounter with a giant planet could have pushed the comet into an extremely distant orbit, while another sufficiently powerful interaction could have released it completely from the gravity of its parent star. If 3I Atlas left its birthplace early, most of its existence may have unfolded not within a planetary system, but in the darkness between the stars. Yet an ancient object did not necessarily spend the entire span since its formation wandering through interstellar space. It may have remained around its parent star for billions of years before a disturbance finally cast it outward. Or it may have departed while the system was still young, spending most of galactic history as an object belonging to no star at all. Its chemical composition can help estimate the era in which it formed, but it does not clearly record the moment when it was expelled. Between those 2 points lies an immense blank space that the light we observe today cannot fully read. The parent star itself may also have changed dramatically since 3I Atlas formed. If it was more massive than the Sun, its life may have ended long ago, leaving behind a white dwarf, a neutron star, or some other remnant. If it was a smaller, longer-lived star, it may still be shining somewhere in the Milky Way. But after billions of years of motion, the distance between that star and the lost fragment of cometary ice has become far too great for the connection to be easily restored. The object carries no label identifying its origin, while the galaxy continually turns and mixes its orbits. Tracing it back to one particular star system is almost beyond our present capabilities. That uncertainty does not weaken the value of the discovery. Science often cannot reconstruct the past in full, but it can establish reliable limits on what may have happened. The carbon ratio does not reveal the name of a star, but it suggests that the material may come from an era when the Milky Way contained less carbon. 1-3. Deuterium does not provide a date, but it tells us that the ice passed through an extremely cold environment and avoided prolonged heating. The orbit does not retrace the object's entire former path, but it confirms that it arrived from beyond the solar system. 3 different clues converge on the same image: a comet born far away, during an age that may predate our home by billions of years. When 3I Atlas is placed beside the Sun, the contrast is not one of size, Our star is so much larger than this body of ice that any physical comparison nearly loses its meaning. The contrast lies in time. The sun is now in the stable middle period of its life and will continue shining for billions of years. Yet the material within this small visitor may have existed long before the star itself was born. One of the smallest objects observed within the solar system may carry a history longer than that of the brilliant center now awakening it. The ice of 3I, Atlas, does not allow us to see the Milky Way as it appeared 10 billion years ago. It preserves no images of ancient stars, records no positions of galaxies, and does not recount the complete history of its parent system. What remains is far more subtle: an unusual abundance of deuterium, a low carbon 1:3 ratio, and a combination of molecules that has crossed an immense span of time without being completely erased. From differences this small, science reconstructs part of the background of a vanished age. In the sun's present light, the gas surrounding the comet exists only temporarily. Molecules leave the surface, spread into the coma, and gradually disperse. Yet that brief moment is enough for a silent object to bring the galaxy's past closer than any distant ancient star. Stars from cosmic noon are usually observed through light that has traveled for billions of years. 3I, Atlas, by contrast, carries material from a similar era directly into the neighborhood of the Sunday. A small comet has passed through our home, and within its composition, the solar system suddenly seems much younger. The sun remains the center of every familiar orbit around us, but it is no longer the beginning of this story. Before its light, there were other stars, other cold clouds, and planetary systems that may have formed, changed, and disappeared, leaving behind a fragment of ice that continued drifting until the day it encountered us. By this point, 3I, Atlas, is no longer merely an unusual point of light recognized by its unexpected orbit. With each new layer of observation, that first image has gradually gained depth. Its trajectory shows that the sun cannot hold it. The cloud of gas surrounding it confirms that it is a comet being warmed. Light passing through that gas carries the signatures of water, carbon dioxide, and other volatile substances. Deeper still, the deuterium ratio and the relative scarcity of carbon, 1:3 point toward an extremely cold formation environment, possibly one belonging to a much earlier stage in the history of the Milky Way. Each clue provides only a small piece, but when they are placed together, they form a more consistent picture. The object now crossing the solar system was not born alongside Earth, and its history may have begun before the sun existed. That consistency matters, because no single measurement is capable of telling the complete story of an interstellar comet's origin. Its orbit reveals that the object came from outside, but it cannot describe the environment where its earliest ice formed. Deuterium reflects reactions that occurred under cold conditions, yet it does not record a precise age. The carbon ratio adds context about the chemical evolution of the Milky Way, but it must still be compared with models and with other components. Science approaches the past not through a door that opens all at once, but through many narrow slivers of light, each revealing a different part of a room hidden by time. What has appeared through those slivers is already enough to rule out several simple explanations. This is not a comet from the distant edge of the solar system that happened to fall into an extremely long orbit. Its speed and trajectory show that the sun was never the original gravitational center of its motion. Its chemical composition also does not fit easily within the familiar range of comets from the Oort cloud or the Kuiper belt. Although the objects within our own home display considerable diversity, the isotopic signatures of 3I, Atlas still point toward a different history, shaped beneath the light of another star, or perhaps within a cloud of gas that existed before that star was born. Yet there remains an enormous distance between recognizing a foreign origin and reconstructing the object's entire life. Chemistry can preserve an environment, but it does not record an address. The current orbit allows astronomers to calculate its path through the solar system with great precision. But when that path is extended backward over millions of years, the small influences of stars, clouds of gas, and the Milky Way's gravitational field begin to accumulate. A tiny uncertainty in the present can grow into an immense distance when traced too far into the past. After billions of years, finding the correct parent star would be almost like trying to identify the exact beach from which a single grain of dust once came, after it had traveled through countless currents and seasons of wind. For this reason, most of the birthplace of 3I, Atlas, remains hidden in darkness. There is no named star to place beside it, no image of the disk of gas and dust in which it once grew. We cannot know whether the object formed in the outer region of an ordinary planetary system, within a binary star system, or in a crowded environment where many young stars were born close together. Its chemical ratios narrow the range of possibilities, but they cannot yet turn its birthplace into a complete landscape. We see only traces of the cold, the degree of isotopic enrichment, and a history that may be extremely ancient, much as we might infer the climate of a distant land from dried mud clinging to an object, even though no map remains to show where that land once lay. The next uncertainty concerns the moment when the comet left its parent system. An object may be older than the Sun without having wandered between the stars for that entire span of time. It may have formed very early, then remained in the outer reaches of its planetary system for billions of years before a gravitational disturbance finally cast it away. Or the separation may have occurred while the system was still young, during an age when giant planets were migrating and orbits had not yet become stable. These two histories lead to the same result today: a free object traveling through interstellar space. Its chemical composition cannot easily distinguish a quiet existence around its parent star from a long passage through the darkness between stars. Even the age of the ice is not necessarily the same as the age of the comet as a single, unified object. Some of its water and organic molecules may have formed within the molecular cloud before the parent star was born, then been carried into the emerging disk. Older material would later mix with newer material, gather into larger grains, and eventually become part of a cometary nucleus. In this way, some molecules inside the object could be older than the structure that brought them together. When Webb reads its spectrum, it is examining a mixture of many stages, not a sample created all at once. This complexity is not a flaw in the research. It reflects the true way planetary systems form. Nature does not divide the past into clean chapters, each with a clearly marked beginning and end. Matter is reused, mixed, moved, and assembled again. Ice from an older cloud may lie beside molecules newly formed within a younger disk. A comet can preserve both, then endure collisions, lose its surface layers, gather additional dust, and finally leave its system altogether. What humanity observes now is the final result of that entire sequence, compressed within a small nucleus, slowly releasing material beneath the sun's light. Another limitation comes from the moment of observation itself. As 3I, Atlas, is warmed, the escaping material may not represent the entire nucleus evenly. Surface regions receiving more heat will become more active. Some pockets of ice may release gas first, while deeper layers remain sealed. The composition of the coma therefore reflects the material being exposed at that particular time, rather than a perfectly blended sample of the whole comet. Observations made at different stages help reduce this limitation, but they cannot remove it completely. The sun both allows us to see the material inside and determines which parts of the object are revealed first. Even so, these limitations do not return the story to its original uncertainty. Several conclusions remain fairly secure. 3I, Atlas is traveling on an interstellar trajectory, so it does not belong to the solar system. It displays the characteristic activity of a comet, with ice sublimating and producing a surrounding cloud of gas. The chemistry of that gas differs clearly from the range usually observed in comets around the sunday. Its isotopic ratios are consistent with an origin that was extremely cold and possibly very ancient. What remains unknown lies in the details of its history, not in the interstellar nature of the object itself. That distinction brings the entire picture into better balance. Science does not need to know everything before it can say something meaningful. A person standing at the edge of the sea does not need to trace every drop of water back to the place where it evaporated to know that a wave has arrived from offshore. Its current, its salinity, and the material it carries are enough to show that its origin lies beyond the shallow water near the beach. For this comet, its orbit and chemistry serve a similar purpose, confirming that it entered the sun's domain from a history outside the familiar population of objects surrounding us. Looking back across all the evidence gathered so far, the image of 3I, Atlas, has become both clearer and broader. Clearer, because it has been identified as an interstellar comet with measurable chemical characteristics. Broader, because every observation connects this small object to star formation, isotopic evolution, and the billions of years that shaped the Milky Way. A faint point of light now carries links to ancient molecular clouds, vanished generations of stars, and planetary systems humanity has never seen. Yet one stage of its history has not been fully explored. Wherever it formed, and however ancient it may be, this object once lived under the influence of a star. It must have followed an orbit, occupied a region of motion, and held some place within its parent system. To become a wanderer between the stars, it had to escape the gravity that once held it there. Space does not simply take a comet orbiting one star and place it into the galaxy. Some process must have been powerful enough to change its velocity, reshape its path, and push it beyond the gravitational boundary of its home. That process may have unfolded during the most chaotic period in the life of its planetary system, when large worlds had not yet settled into stable positions, and countless small bodies of ice were continually being drawn onto new trajectories. A giant planet could have given the comet additional speed during a close encounter. A companion star might have disturbed the system's outer regions. Another star passing close enough could also have destabilized distant orbits. Each mechanism would leave behind a different history, but all of them open the same path of escape, from a member of one planetary system to a free object of the Milky Way. Somewhere in the distant past, 3I, Atlas passed through that opening. An orbit that had once been closed no longer returned upon itself. Its parent star gradually receded, its light grew faint, and the object entered a region of space where no single center governed its motion. The ice still carried the chemical traces of the environment in which it formed, but its gravitational connection to home had been severed. That unseen moment transformed an ordinary comet from a distant system into the visitor the solar system encounters today. Looking at the solar system today, every motion seems to have settled into a stable place. Earth completes one orbit around the Sun each year, Jupiter follows a wider path, and most distant comets remain in the cold regions beyond the planets. That regularity can create the impression that a planetary system always forms in an orderly way and then preserves the same structure for the rest of its existence. But during the first few million years, when the planets were still incomplete and billions of fragments of rock and ice crowded the disk around the young star, the scene may have been entirely different. It was an age of intersecting orbits, close encounters, and sudden changes in which a single gravitational interaction could determine the fate of a small object. 3I, Atlas may once have belonged to a setting like this. Within its parent system, the small body probably began in a cold region where ice could survive for long periods, and dust grains gradually gathered into larger masses. When it first formed, it was not yet a wanderer. It traveled around a star, felt the influence of growing planets, and shared its surroundings with countless other fragments of material. Its original orbit may have been nearly circular or more elongated, but it was still a closed path. After every revolution, it returned to the same region, remaining within the gravitational system that had created it. That stability did not necessarily last. Within a young planetary disk, large worlds do not always form in their final positions and remain there. They absorb gas, collide with smaller bodies, exchange momentum with their surroundings, and may shift their orbits significantly. A giant planet, especially one with a mass similar to Jupiter or greater, creates an enormous region of gravitational influence. Any comet passing through that region can be pulled off course, redirected, and sent away from the encounter at a different speed than before. Gravity during a close approach does not act like a direct push from behind. The comet falls into the planet's gravitational field, accelerates as it draws near, and slows again as it moves away. If the planet were standing still, the object might leave with almost the same speed it had before, though its direction would be different. But the planet is also orbiting its star at tremendous velocity. From the star's frame of reference, the comet can take away some of the planet's orbital energy or give some of its own energy back. The exchange is almost insignificant for the giant world, yet it can completely transform the path of a body millions of times lighter. Humanity now uses this same principle to send spacecraft into the distant solar system. A probe passing a planet at a carefully calculated angle can gain speed without burning an equivalent amount of fuel. This technique is commonly called a gravity assist. In a young planetary system, comets experience natural gravity assists as well, except that no one chooses the angle of approach or controls the result. Some bodies are thrown inward toward the star, others are transferred into longer orbits, and a small number gain enough energy never to return. The boundary between remaining and escaping does not appear as a glowing line in space. It is determined by the object's energy of motion compared with the gravitational pull of the star. If a comet has not gained enough speed, its path will still curve into a closed orbit, even if the new journey takes thousands or millions of years to complete. If its velocity rises beyond what is needed to escape the system, that curve opens. The star continues pulling on the object and slowing it across an enormous distance, but can no longer force it to turn back. A slight change during one close encounter can transform a returning orbit into a one-way path. Perhaps the most important moment in the history of 3I, Atlas unfolded without any brilliant display. It did not need to collide with a planet or pass through an explosion. The object may simply have swept past a massive world at a sufficiently close distance, entered a stronger region of gravity, curved through part of its path, and then departed in a new direction. The parent star remained where it had always been, shining as before, but the comet's trajectory had changed. With every hour, every day, and every year after that encounter, the distance between them increased, until the star's light became only one small point among countless others. A giant planet is not the only path outward. If the parent system contained two stars, its gravitational structure would have been far more complex. Distant objects could have felt forces that changed with the motion of both stars, gradually making their orbits more elongated or unstable. A comet that once rested in the quiet outer region might have been drawn inward, encountered a large planet, and then been expelled through a sequence of interactions. In some cases, the two stars themselves could provide enough energy for the object to escape without the involvement of a planet. The environment in which the star was born may also have played an important role. Stars do not usually form in complete isolation. Many young stars emerge within the same cluster, separated by much smaller distances than those between the Sun and its neighboring stars today. While the cluster remained dense, another star could have passed close enough to disturb the outer orbits of the system. Objects moving slowly in those distant regions are especially sensitive to such influences because the gravitational hold of the parent star is already much weaker there. A single stellar passage could pull some comets farther outward, push others inward, and release a fraction of them from the system entirely. The departure may not have been caused by one event alone. 3I, Atlas could have experienced several changes in orbit before finally escaping its home. At first, a planet may have pushed it from the cold outer region into a more elongated path. After thousands of revolutions, a passing star may have shifted the farthest point of that orbit. Later, another planetary encounter could have added just enough energy to complete the escape. Each interaction may have altered the path only slightly, yet together they could have carried the object beyond the limit of what its parent star was able to retain. In a crowded planetary system, expulsions like these are not unusual. Planet formation does not use every fragment of material within the disk. After large worlds appear, countless bodies of rock and ice continue moving among them. The planets gradually clear their orbital regions by absorbing smaller objects, colliding with them, or scattering them elsewhere. Some remain stored in the outer system, some fall toward the star. Others are pushed away entirely, carrying with them the chemical materials once created within the original disk. The solar system itself probably lost many objects in much the same way. As Jupiter, Saturn, and the outer planets shifted their positions, their gravity may have sent countless icy bodies into interstellar space. Those objects are now drifting somewhere in the Milky Way, so far from the Sun that they can no longer be considered members of the solar system. One of them may even be passing through another planetary system at this very moment, appearing as a foreign visitor to imagined observers there, just as 3I, Atlas, now appears through our telescopes. This picture changes our understanding of the space between the stars. That vast region is not entirely empty. Along with extremely diffuse gas and dust, the galaxy may contain enormous numbers of free-floating planets, asteroids, and comets that have lost their stars. Most are too small and too dark to be detected. They reflect only tiny amounts of light, and their distances from Earth are usually immense. Only when an object happens to pass close to a star, receives enough illumination, and begins to become active does it have a chance to emerge from observational darkness. Although the mechanisms of ejection are now modeled in considerable detail, there is still no way to know which one acted upon 3I, Atlas. No direct trace remains of the planet that may have altered its course if such a planet ever existed. Its chemical composition cannot tell us whether it was thrown outward by a giant world, a companion star, or a close encounter within a stellar cluster. Each mechanism can produce different distributions of velocity, but after immense spans of time under the influence of the Milky Way's gravitational field, many of the original signatures become blurred. Its present velocity still provides part of the story, though not the whole of it. From the path of 3I, Atlas through the solar system, astronomers can determine the speed it carried before feeling the sun's gravity in a significant way. That value confirms that the object arrived in an unbound state, but it cannot easily be traced back to the speed it possessed when it left its parent system. Over millions or billions of years, its motion around the center of the galaxy, its passages through regions of varying stellar density, and countless tiny gravitational influences have continually adjusted its trajectory. The moment of separation remains too distant to reconstruct in full. An object expelled from a system does not instantly lose the influence of its parent star. For a time, it still travels through the outer regions, where the star has become only a point of light, yet its gravity has not completely disappeared. The object's escape speed gradually decreases as it climbs out of the star's gravitational well, much like a stone thrown upward slows as it rises. The difference is that the stone has been given enough energy not to fall back. After an immense journey, the pull of the parent system becomes weaker than the combined gravitational influence of the galaxy itself, and the comet enters a state in which it no longer belongs to any single star. That transition does not create a clear boundary, either. There is no gate marking where a planetary system ends and interstellar space begins. The density of the stellar wind fades gradually, the light grows dimmer, and the star's influence blends into the broader gravitational field of the Milky Way. Home does not vanish suddenly. It recedes little by little, until the star that once governed every orbit becomes just another point of light among many others in the sky of the object. If 3I, Atlas departed while its parent system was still young. It may have carried ice that had not experienced many close passages by its star. That would allow some of its original cold chemistry to avoid extensive reprocessing. On the other hand, if the ejection happened much later, the comet may have spent billions of years in the outer regions before a final disturbance set it free. Both histories are consistent with an object carrying extremely ancient signatures, and the current data is not sufficient to choose between them. Even if its specific history remains hidden, one point can be imagined with some clarity. 3I. Atlas did not decide to leave. Its orbit was rewritten by gravity, a force with no intention of its own, yet one capable of transforming the fate of matter entirely. A slightly closer encounter, a planet in just the right position, or a passing star arriving at the right moment could have made the difference between billions more years circling its birthplace and a journey with no path back. After escaping its parent system, the object no longer received periodic warming from its original star. The light gradually faded, the surface temperature fell, cometary activity subsided, and the cloud of gas that once surrounded the nucleus dispersed into space. 3I. Atlas returned to a state that was dark, cold, and nearly impossible to detect. Volatile molecules remained locked within the ice, while its new trajectory carried it across distances far greater than any path it had once followed around a star. Behind it, the planetary system continued evolving without the lost fragment of ice. The planets settled into greater stability, the disk of dust gradually thinned, and the surviving bodies found long-term orbits. Ahead, there was no predetermined destination. There was only the broad gravitational field of the Milky Way, stars scattered across enormous distances, and a journey so long that most of its history left no direct trace at all. A comet that once belonged to a planetary system had become an object of interstellar space. The memory of its birthplace remained preserved within the ice, but the star that once illuminated that place had faded from view. Only after a span that may have lasted millions or even billions of years did 3I. Atlas encounter another star close enough to awaken the material on its surface. That star was the Sunday, yet before that brief encounter lay a far longer voyage, during which this ancient visitor traveled through the darkness while belonging almost nowhere at all. After leaving its parent star system, 3I, Atlas did not immediately enter a realm of perfect emptiness. Around it there was still the light of countless stars, extremely thin interstellar gas, tiny grains of dust, and the vast gravitational field of the Milky Way. Yet compared with the planetary disk that had once held the object in a familiar orbit, this new environment was so enormous that it almost had no clear center at all. The old star receded, its warmth faded, the gas surrounding the comet disappeared, and the surface returned to a dark, frozen state. Molecules that may once have escaped during close passages near its star became locked again inside the ice, while the cometary nucleus continued moving with the velocity it had received in the moment it was cast away from home. Interstellar space is often imagined as an absolute void, but in reality, it still contains matter. Its density, however, is far lower than almost any environment familiar on Earth. In a volume where our atmosphere would contain countless molecules, an interstellar region may hold only a few atoms. An object like 3I, Atlas could travel for a very long time without encountering any body large enough to significantly alter its course. Most collisions would happen on a microscopic scale, between the comet's surface and tiny dust grains or atoms moving through the galaxy. That emptiness creates a different kind of quiet. There is no air to carry sound, no weather, and no day and night in the ordinary sense. No side of the comet faces any nearby light source strong enough to create a clear thermal cycle. Its surface temperature falls deeply, volatile substances almost stop escaping, and the activity that once made the object appear as a comet temporarily disappears. If a distant telescope happened to look in its direction, 3I, Atlas would likely be nothing more than a dark point too small to recognize, without a bright coma and without a faint tail stretching behind it. Its motion continues, needing no fuel and no sustained push. In a vacuum, an object that already has velocity does not slow down on its own the way objects do when moving through air. Only distant gravitational forces gradually alter its direction. Each star pulls on it slightly, but across most of its journey, those forces are too weak to create an obvious turn. Over short timescales, the comet seems to travel in a straight line. Over millions of years, that path becomes part of a much larger motion around the center of the Milky Way. The Sun is part of that motion as well. The entire solar system orbits the galactic center, carrying the planets, comets, and all matter held within its gravity. Other stars also move along their own orbits. They are not fixed against an unmoving background. After losing its parent star, 3I, Atlas still belonged to the Milky Way in a broader sense. It was held within the galaxy by the combined gravity of hundreds of billions of stars, gas, dust, and dark matter, even though it no longer orbited any particular star. So, wandering between the stars does not mean moving without direction. The object still drifts around the center of the Milky Way along with other galactic material, like a small leaf carried in a vast current. It has its own velocity, its own direction, and its own history, but the entire flow remains shaped by the structure of the galaxy. Spiral arms, dense gas regions, star clusters, and passing stars can all adjust its trajectory very slowly. Most of these changes are far too small to notice in a human lifetime, but across hundreds of millions of years, they can carry the object into entirely different regions. If 3I, Atlas truly originated during a very early period in the Milky Way's history, it may have completed many journeys around the galactic center before encountering the Sunday. Each of those circuits lasts longer than the entire history of many species on Earth. During that time, spiral arms did not preserve the same shape. Clouds of gas collapsed to form new stars, and star clusters gradually dispersed into separate points of light. The small object kept moving, carrying its ancient ice through a galaxy that was continually changing around it. No one can reconstruct every part of that path in full. Its current orbit allows us to trace it backward, only for a limited time before uncertainties become too large. Each time a star passed by at a relatively close distance, its gravity could have shifted the object's direction slightly. Without knowing the exact positions and velocities of every star it encountered in the past, the old path quickly branches into many possible histories. After millions of years, small deviations accumulate, making the original home almost impossible to identify from present motion alone. Most of the object's interstellar life probably did not contain any major event. It did not constantly fly close to stars, nor did it often pass through dense clouds. The distances between star systems are too vast, and the comet itself too small. For millions of years, the surrounding scene may have changed only as certain points of light slowly grew nearer and then receded again. A star might have appeared prominent in the object's sky for a time, but if the distance still measured in light years, the heat it received would have been far too weak to awaken the ice. Occasionally, 3I, Atlas may have crossed a region containing slightly more gas and dust. Tiny particles could have struck its surface at high speed, leaving changes too subtle to see directly. Cosmic rays may have penetrated the outer layers, breaking some chemical bonds and creating new complex molecules. Over long periods, the surface may have grown darker, harder, and different from the more primitive ice buried beneath it. This is one reason a comet cannot be treated as a perfectly sealed box. Its interstellar journey still writes new traces onto it, though that writing unfolds slowly and is usually concentrated near the surface. High-energy particles can penetrate more deeply than ordinary light, but they still do not easily erase all original information. A sufficiently large nucleus can shield the material inside, preserving water, carbon dioxide, and many other compounds over immense spans of time. The surface layer, which receives the strongest effects, can even become a protective crust for the deeper interior. When the object eventually passes close to a star, heat begins to move inward and gradually opens layers of ice that may never have directly touched the interstellar environment, allowing ancient molecules to escape in a less altered state. This makes an encounter with a star a special moment in the life of a free comet. For most of its existence, the object is nearly impossible to observe. Only when it comes close enough to a source of light does the surface begin to warm, gas begin to escape, and a coma appear. The dark object suddenly gains a much larger reflective area, becoming a point of light that survey systems can record. The encounter with the Sun did not create 3I, Atlas, but it made the object visible to humanity after a long stretch of darkness. The probability of an interstellar comet entering the favorable region of a planetary system is very small for any individual object. The space between stars is too vast, while the region close to a star occupies only a tiny fraction of it. Yet if planetary systems have ejected enormous numbers of objects throughout the history of the Milky Way, rare encounters can still occur. Most bodies pass by at distances too great to be detected. Some come closer but remain too small or too dark. Only a few have the right orbit, size, and timing for human observers to notice them. 3I, Atlas belongs to that small group. It was not aiming for the solar system, nor was it guided by any force with a predetermined purpose. The motion of stars, the galaxy's gravitational field, and the object's own trajectory simply brought these paths near one another by chance. In a space filled with countless overlapping motions, two unfamiliar histories crossed for a short time: a comet from another system and a younger star carrying its planets with it. From far away, the Sun's influence at first was only a very slight pull. 3I, Atlas continued along its interstellar path, but its trajectory began to bend gradually toward this new gravitational region. The closer it came, the more its speed increased. The Sun could not capture the object because it already carried too much kinetic energy, but it could still bend its path and change the direction in which it would eventually leave the solar system. An open orbit formed, carrying the comet through the inner region before leading it back into the space between the stars. Before the ice began responding in a noticeable way, the object had already passed through the outermost regions of the solar system, where the Sun appeared only as a bright point among the stars. It traveled through the realm where objects of the Oort cloud may exist, yet it never became a member of that population. On a map of positions, an interstellar comet and a native comet might appear in the same distant region, but their histories of motion are entirely different. One remains bound to the Sun in an extremely long orbit. The other is simply passing through the star's sphere of influence. As the distance continued to shrink, the Sun gradually became the dominant source of energy affecting the surface. Volatile substances with lower sublimation temperatures began escaping first. Carbon monoxide and carbon dioxide can become active at distances where water ice still remains relatively stable and frozen. The object, once nearly chemically dormant, began producing a thin envelope of gas. Though the activity was still weak, it marked the end of a completely dark drift and the beginning of a phase in which the comet once again took on a recognizable form. That transition did not happen in a single moment. Some parts of the surface received more sunlight, while others remained in shadow, and the deeper ice responded more slowly than the outer layers. Small jets of gas may have emerged from weaker regions, carrying dust into space. Over time, the coma expanded, obscuring the nucleus and making the object appear brighter than its true size. It was this cloud of gas and dust that allowed humanity not only to see 3I, Atlas, but also to begin reading the material preserved from a distant and unfamiliar environment. The moment the object entered the Sun's illuminated region may have been the first time in an extremely long period that it received enough heat to become strongly active. There is no way to know whether 3I, Atlas had ever passed close to another star before. A previous encounter might have stripped away part of its surface, while billions of years without a nearby source of heat would have helped preserve the deeper layers of ice. Current observations do not reveal the full history of its past warmings, but the unusual nature of its chemical composition suggests that at least some of its ancient signatures have. On Earth, its arrival was recognized during an interval that was extraordinarily brief compared with the object's entire lifetime. Telescopes recorded the first positions, its orbit was calculated, and deeper observations were quickly organized before the opportunity slipped away. For humanity, this was a rare discovery unfolding over months or years of study. For the comet, it was only a tiny segment between two vast stretches of interstellar darkness. After the encounter, 3I, Atlas will once again leave the warm region behind. The coma will gradually fade, the escape of gas will slow, and molecules that have not yet been released will remain locked within the nucleus. The sun will recede into the distance, becoming another point of light among countless stars. The object will carry with it an orbit that has been bent by the encounter and a surface that has been altered by the sun's warmth, then continue moving through the Milky Way without any predetermined destination. Yet this passage will not disappear entirely. Some of the comet's material has already separated from the nucleus and remains within the solar system as an extremely diffuse cloud of gas and dust. More importantly, the light collected by telescopes has been transformed into data, preserving its composition, its trajectory, and the clues pointing toward an ancient origin. The visitor will continue on its way, but the brief moment when it emerged into the sun's light has been preserved in another form. For most of its history, 3I, Atlas belonged to no particular sky. It traveled through the galaxy as a dark fragment of ice, carrying the memory of its birthplace, while no longer receiving light from its original star. Then, through an extraordinarily rare crossing of paths, it came close to the solar system, where its frozen layers began to awaken and ancient material became observable. After millions or perhaps billions of years of leaving almost no trace at all, this visitor finally entered the light of a star far younger than itself. Before entering the inner regions of the solar system, 3I, Atlas hardly resembled a comet in the familiar sense. There was no bright cloud of gas surrounding it, no long tail stretching behind it, and no obvious stream of dust reflecting sunlight. For most of its journey between the stars, it existed simply as a dark, frozen nucleus, where water and many volatile compounds remained locked within the structure of the ice. That state may have persisted for spans of time far greater than the entirety of human history, until a nearby source of heat finally began to alter the balance at its surface. This time, that source of heat was the Sunday. From great distances, the star's light raised the temperature only slightly, not enough to activate all of the ice at once. Yet not every substance within a comet requires the same amount of warmth to become gas. The most volatile molecules can begin escaping while the object is still far beyond Earth's orbit, whereas water generally needs to come closer to the sun before sublimating strongly. Cometary activity, therefore, does not switch on like a lamp. Instead, it unfolds gradually with distance, as different materials respond at different stages of the journey. Carbon monoxide and carbon dioxide can escape from ice under colder conditions than water. As 3I, Atlas moved deeper into increasing sunlight. These compounds may have produced the first streams of gas, emerging through cracks and porous regions on the surface. The escaping gas carried tiny dust grains with it, lifting them away from the nucleus and dispersing them into space. At first, this material was too sparse to create a recognizable appearance. Over time, however, the amount of released gas increased, the region surrounding the nucleus expanded, and the comet began to appear brighter than a solid body of the same size. The process of sublimation does not occur evenly across the entire surface. As 3I, Atlas rotates during its journey, different regions take turns facing the Sunday. One area may remain illuminated for hours, releasing gas more actively before cooling again as it rotates into darkness. Regions covered by thicker layers of dust may respond more slowly, while a newly opened crack can allow heat to penetrate deeper and release material more rapidly. The coma forms from the combined effect of countless small changes like these, continuously replenished near the nucleus and gradually expanding as gas and dust drift away. Beyond the coma, the solar wind and the pressure of sunlight begin organizing the material in two different ways. Ionized gas is swept away by magnetic fields carried within the solar wind, forming a plasma tail that can change rapidly as surrounding conditions vary. Heavier dust particles respond more slowly, retaining part of the comet's orbital motion and creating a broader, curved dust tail. Both structures originate from material inside the nucleus, yet once released, they quickly become part of the solar system's environment. For 3I, Atlas, the expanding cloud of gas carries a significance that goes far beyond the appearance of an active comet. Within every stream of escaping material are molecules that spent most of the object's history beneath its surface. Some may have formed within the molecular cloud that existed before its parent star was born. Others may have originated within the planetary disk surrounding that star. Together they left their home system, crossed interstellar space, and eventually entered the light of a different star. The sun did not create that chemical history. It merely released a history that had been preserved within the ice. That release follows a sequence that is far from simple. The outermost layers, exposed to cosmic radiation throughout the interstellar journey, may have become darker and more hardened over time. The compounds found there do not necessarily represent the deeper interior. As heat gradually penetrates downward, less altered regions begin contributing to the activity. The composition of the coma can therefore shift over time, reflecting different layers of ice being exposed. For this reason, a single observation reveals only the comet's condition at a particular moment, while a sequence of observations before and after its closest approach to the sun is needed to identify more enduring signatures. The timing of James Webb's observations was especially valuable because 3I, Atlas, had been warmed enough by the sun to produce gas that could be analyzed, while still remaining in a favorable position for the telescope. Had the comet been much farther away, the coma would have been weaker, and many compounds might have remained below the threshold of detection. Had it been observed too close to the sun in the sky, intense sunlight and observational constraints could have made data collection much more difficult. The period after the comet's closest approach allowed Webb to observe an object that was clearly active while gradually moving away from the brightest region. During this outward journey, the nucleus does not cool immediately. Heat that has already penetrated beneath the surface continues driving the release of gas, even as the intensity of sunlight begins to decline. This creates a delay between distance and activity. Two comets at the same distance from the sun but on opposite sides of their closest approach may behave differently, because the one moving away has already accumulated heat within its interior, while the one approaching may not yet have warmed to the same depth. That delay gives scientists access to material that was not released during the earliest stages of activity. As heat travels deeper, it can reach pockets of ice hidden beneath altered surface layers, opening pathways for gases with compositions different from those found at the surface. Webb's measurements do not provide a direct cross-section through the nucleus, but the changing nature of the coma over time offers an indirect view into its interior structure. If a particular chemical ratio remains consistent through multiple stages of activity, it is more likely to represent a broad characteristic of the object. If the signal changes, the comet may contain regions that formed under different conditions or experienced different histories of processing. In this encounter, the sun serves both as a source of illumination and as an agent of change. Sunlight allows molecules within the coma to leave spectral signatures, yet heat also causes the comet to lose material. Every second of activity releases a small amount of ice and dust that can never be recovered. Most of that loss is tiny compared to the total mass of the object, but the surface that emerges from the encounter will not be exactly the same as the one that entered it. Porous regions may collapse, layers of dust may accumulate where gas escapes less efficiently, and new fractures may open because of changing temperatures. If 3I Atlas has passed close to another star in the distant past, its surface may still carry traces of that earlier warming. Current observations are not sufficient to fully reconstruct such encounters. The object may have spent most of its existence without approaching any significant heat source, or it may have passed through one or more stellar systems closely enough to alter its outer layers. What Webb observes today is the result of that entire history combined with the response currently unfolding beneath the sun's light. The original and the altered are not separated into perfectly distinct layers, yet the unusual isotopic ratios suggest that part of the older memory remains preserved. While telescopes collect their light, the coma itself does not remain still around the nucleus. Gas that has only just escaped immediately begins expanding outward, its density dropping rapidly with distance, while solar radiation can break some molecules into smaller fragments. The substances detected in spectra are sometimes molecules released directly from the ice, and sometimes products formed after a parent molecule has been split apart by sunlight. Distinguishing between these sources requires modeling reaction rates, gas flow directions, and the distance between the observed signal and the nucleus. By studying how various compounds are distributed throughout the coma, scientists can infer which materials were released directly and which formed later as the cloud expanded into space. James Webb has a major advantage in the infrared region of the spectrum, where many molecules leave especially clear signatures. NIRSpec separates light into highly detailed spectra, making it possible to identify absorption and emission features associated with water, carbon dioxide, carbon monoxide, and rare isotopes. The telescope does not see individual molecules, but it records the combined effect of vast numbers of molecules existing within its field of view. From a cloud of gas, far too diffuse for humans to perceive directly, patterns in the light are transformed into measurements of composition and abundance. The subtlety of this measurement stands in striking contrast to the scale of the story it reveals. The coma exists only because the comet passes near the sun for a brief period of time. The light collected by Webb may represent only a few hours of observation. Yet the molecules responsible for those signals may have remained locked in ice for billions of years. A very short window of human observation touches a history nearly as old as the Milky Way itself, not by looking farther into the distance, but by reading material that has briefly entered our cosmic neighborhood. As 3I Atlas moves away from the sun, its activity will gradually decline. The sunlight weakens, temperatures fall, and the remaining volatile compounds once again become trapped within the nucleus. The coma disperses and blends into the interplanetary environment. The tail fades until it can no longer be distinguished, and the object returns to the dark form it carried during its journey between the stars. The sun awakens only part of the ice. It does not open the entire archive preserved within. The material that remains unreleased will continue outward with the comet, perhaps lying dormant for another immense span of time. Each time a comet approaches a star, it both reveals and loses part of its history. For comets belonging to the solar system, that process may repeat through many orbital cycles. 3I Atlas has no such return journey. Its open trajectory will carry it beyond the sun's influence and back into interstellar space. The opportunity to observe its ice becoming active beneath the light of our star happens only once, making every spectrum collected a piece of data that can never be reproduced under exactly the same conditions. The encounter is still gentle enough for the object to continue on its own path. The sun bends its orbit, accelerates it as it approaches, and slows it again as it departs. But it cannot hold this visitor in a new cycle around the star. The surface is altered. Some material is left behind, yet the nucleus retains enough energy to escape. Once the illuminated region recedes into the distance, 3I Atlas will again become a dark point that is almost impossible to detect, except that this time it will carry the traces of its encounter with the solar system upon its surface. During that brief interval between two long periods of cold darkness, the Sun transformed a portion of ancient ice into gas, and Webb transformed the light from that gas into data. Molecules that had remained locked away for billions of years appeared in the coma for only a short time before dispersing. Yet that was enough to make the object's distant origin more clearly visible. Our star is not where 3I Atlas was born, but its light has allowed this visitor to reveal what it still carries from another star system. For a very long time, the solar system was not only humanity's home, but also the only model we had for imagining how a planetary system might be built. The Sun sits at the center. Rocky planets lie closer in. Giant gaseous worlds occupy wider outer orbits, and asteroids and comets preserve material that never became planets. Before we could clearly observe other star systems, this familiar structure was easy to regard as the common shape that nature tends to create. Discoveries of exoplanets gradually changed that view. Around distant stars, there are giant gas planets orbiting very close to their light sources, worlds larger than Earth but smaller than Neptune, and systems where many planets are packed into a narrow orbital region. Some of these structures have no clear equivalent around the Sunday. The laws of physics remain the same, but the final results can be arranged in far more ways than our own home once suggested. Most of those worlds are known through their size, mass, or influence on the light of their star. Smaller objects in the outer regions of a system, where ice and dust preserve traces of the earliest stages of formation, are much harder to observe. A comet around a distant star is usually too small and too dim to be recognized from Earth. So when a fragment of ice is thrown from its parent system and happens to pass through the Sun's neighborhood, humanity receives a very different kind of opportunity. Not only to know that another planetary system once existed, but to read part of the chemical composition of material created there. This interstellar visitor does not bring unfamiliar elements. In the gas around it, there is still water, carbon dioxide, and many compounds already familiar from comets in the solar system. The difference lies deeper, in the ratios between isotopes of the same element. Its high deuterium abundance and relatively low amount of carbon, 1,3, suggests that the ice formed under colder conditions and may also belong to an earlier stage in the chemical history of the Milky Way. That difference is like another landscape that also contains rock, water, and air, but whose climate has arranged them into a completely different scene. Two planetary systems may be built from the same basic ingredients, while temperature, radiation levels, and the time of formation make their chemical ratios diverge. The unfamiliar does not have to appear as a substance never seen before. Sometimes, it is only a small deviation in water or carbon, durable enough to survive for billions of years. Even within the solar system, comets are not all the same. Some formed in relatively closer regions, while others began in the distant cold and were later moved into new orbits by the giant planets. Their water and volatile compounds reflect different regions of the primordial disk. Even so, they all share a common history around the young Sunday. They are like books written in different rooms, but still belonging to the same library. A fragment of material from outside adds a book that does not belong to that library. It uses the same chemical alphabet, but the characters are distributed in a different order. A single sample is not enough to describe every star system in the galaxy, yet it is enough to remind us that standards built from comets around the Sun cannot automatically represent every place. The idea of what is normal, therefore, becomes harder to define. If a planetary system is considered normal because it forms from a disk of gas and dust around a star, creates planets, and leaves behind countless small bodies, then the solar system may not be especially unusual. But when we look more closely at the positions of giant planets, the number of inner worlds, comet composition, or the history of orbital migration, each system may carry its own structure. What is common lies in the underlying laws, while the final shape depends on many events that never repeat in exactly the same way. A single large planet changing position can rewrite the history of an entire system. It can prevent some small worlds from growing, draw material inward toward the star, or throw icy bodies into interstellar space. A companion star can make the gravitational field more complex. A passing star can disturb the outer regions. The composition of the original cloud, the speed at which the disk disperses, and the brightness of the young star all help determine what kinds of planets and comets are created. If the current chemical signs truly reflect a very ancient origin, then the comparison reaches beyond two different places. It may be a comparison between two eras of the Milky Way. The solar system formed after the galaxy had already passed through many generations of stars, with enough time for carbon and heavier elements to be created and dispersed more widely. A planetary system that appeared much earlier would have begun from raw material with different isotopic ratios, even while obeying the same laws of physics. What seems unusual beside our own comets may once have been more common in a distant age. A lower amount of carbon, 1-3, does not necessarily point to a strange place. It may reflect a time when the interstellar medium had not yet been enriched with that isotope by many generations of stars. In the same way, a high deuterium abundance may preserve the mark of ice formed in deep cold, where material avoided many cycles of heating and reprocessing. This view also helps avoid unnecessary exaggeration. A different composition does not mean mysterious matter or something beyond nature. Deuterium is still hydrogen with an extra neutron. Carbon 1-2 and carbon 1-3 are still two isotopes of the same element. The molecules surrounding the comet were all formed through chemical processes that can be described. The fascination lies in the fact that those same laws operated in a different environment and left behind a result. Unlike the region around the sundae, the presence of water and carbon compounds is also not evidence of life. These molecules play an important role in prebiotic chemistry and can be transported by comets between different regions of a planetary system. But they form naturally in cold clouds of gas without any biological activity. The visitor passing through provides information about ingredients and environment. It cannot yet tell us about the planets that may once have existed around its parent star, much less whether any of them had conditions suitable for life. Its greater value lies in expanding the range of materials that planetary systems can create. If the comet of an ancient system carries a different abundance of deuterium, then planets forming from the same material may also have begun with water ratios unlike Earth's. If carbon was distributed differently, the atmospheres and surfaces of worlds there may have developed along their own paths. We cannot reconstruct an entire system from one lost fragment of ice, but that fragment still shows that the starting materials were not uniform across the galaxy. Perhaps the solar system is ordinary in a broad sense, yet unique in its details. It was born through a common process. A cloud collapsed, a star formed, and a disk of material gave rise to planets. Yet the order of those planets, the position of Jupiter, the amount of water that reached Earth, and the sequence of collisions that followed all belong to a history of their own. Just as trees of the same species can grow into different shapes depending on soil, sunlight, and weather, planetary systems may recognize one another through their underlying structure, while never repeating themselves exactly. To know how common the chemistry of this visitor truly is, humanity will need many more interstellar objects. 3 confirmed examples are still far too small a sample. Moreover, survey systems are naturally better at detecting objects that are larger, brighter, or more active, while smaller and darker bodies may pass through unnoticed. What we know today may represent only the most visible portion of a vast population drifting between the stars. Even if it is still too early to decide whether the solar system is rare or common, this encounter has already changed the way comparisons are made. In the past, every comet studied in detail belonged to the Sun's family. Now, at least one source of material from beyond that family has been analyzed deeply enough to reveal distinct isotopic ratios. For the first time, the solar system can be placed beside a chemical sample that formed within a history entirely separate from its own. That comparison neither diminishes the importance of our familiar home nor elevates it into a uniquely special place within the galaxy. It simply places the Sun, the planets, and our comets within a much larger population. Within that population, each system may begin with the same basic ingredients yet create different worlds. Each fragment of ice may preserve its own kind of memory, and objects once lost from their birthplaces may become rare bridges connecting separate planetary histories. This interstellar visitor carries no verdict on whether the solar system is normal. Instead, it suggests that the answer will not be found in a simple choice between ordinary and exceptional. Our home is part of a process unfolding throughout the Milky Way, yet the way that process unfolded here still bears its own distinctive signature. An ancient fragment of ice from elsewhere has expanded the boundaries of comparison, while leaving the remaining pieces of the story for the interstellar visitors that have yet to arrive. Even a telescope as powerful as James Webb cannot turn distance into direct contact. It can collect faint light from the cloud of gas surrounding a comet as it moves away from the Sun, separate that light into a spectrum, and identify the signatures of many molecules. But it cannot hold a piece of that ice in a laboratory, drill into its deeper layers, or look directly inside the nucleus itself. What we know about this interstellar visitor is built from light, while everything that light does not carry remains beyond a boundary that is extraordinarily difficult to cross. That boundary is not a limitation of Webb, it is the nature of astronomy itself. Distant stars, planets, and clouds of gas are all studied through the radiation that reaches our instruments. Light can reveal temperature, velocity, composition, and sometimes even spatial structure, but always indirectly. Scientists do not observe an individual water molecule inside a comet's coma. Instead, they measure the combined influence of countless molecules on specific wavelengths of light, then use well-tested physics to infer the material responsible for those patterns. For this object passing through the solar system, the most direct data comes from its position in the sky over time. A sequence of observations allows astronomers to calculate its orbit, velocity, and direction of travel. From that information, its interstellar nature becomes clear. Its path is not a closed orbit around the Sun, and its kinetic energy is high enough that it will continue outward rather than return. This is not a conclusion based on appearance or a poetic label. It emerges from orbital mechanics, verified through multiple independent observations. The next layer of information comes from its cometary activity. The faint glow surrounding the nucleus reveals that material is escaping as the surface warms. The distribution of gas and dust shows that this is not an inert rock. Water, carbon dioxide, carbon monoxide, and other compounds leave distinct signatures in the infrared spectrum. The isotopic ratios of hydrogen and carbon add another layer of depth, pointing toward an extremely cold environment of formation, and perhaps a period far earlier than the birth of the solar system itself. These measurements form the strongest foundation of the story. They tell us how the object is moving, what materials it is releasing, and how it differs from the familiar comets that orbit the Sunday. Yet the moment we move beyond what is directly observed, astronomy enters the realm of models and probabilities. An isotopic ratio does not contain the name of a parent star. A molecule carries no map of a billion-year journey. A temporary cloud of gas does not reveal the full structure of the nucleus hidden beneath it. The estimated age of the object provides a clear example. Low carbon, 1,3, and elevated deuterium are consistent with material that formed in an ancient, extremely cold environment that had not yet been heavily enriched by many generations of stars. When these signatures are compared with models of the Milky Way's chemical evolution, they point toward an age that could reach 10 to 12 billion years. Yet this estimate is not equivalent to a direct age measurement, such as dating a rock through radioactive decay. The models depend on assumptions about where the ice formed, how much of the material has been reprocessed over time, and the history of the cloud that gave birth to the parent system. A younger environment that remained exceptionally cold could produce some of the same signatures. Likewise, a very ancient object that experienced repeated heating events might have lost part of its original chemical record. When researchers say the object may be extremely old, that careful wording reflects the true distance between observation and a complete historical reconstruction. Reconstructing the comet's birthplace is even more difficult than estimating its age. Its present orbit can be traced backward for a limited period, but the Milky Way is not a static stage. Stars continually move around the galactic center. Clouds of gas, stellar clusters, and the galaxy's overall gravitational field gradually alter trajectories. A tiny uncertainty in present-day velocity becomes a vast separation when projected backward over millions of years. If the journey spans billions of years, the number of possible paths grows so large that identifying a single parent star becomes nearly impossible. Even if a star with a compatible motion were found, additional evidence would still be required. The star's composition, age, relative velocity, and galactic history would all need to align. The parent star may have drifted far away, evolved dramatically, or even ended its life long ago. If the object formed within a binary system or a dense stellar cluster, determining its origin becomes even more challenging. The chemistry preserved in the ice describes a type of environment, not a specific address. The mechanism that ejected the comet from its home system also remains uncertain. A giant planet may have altered its orbit during a close encounter. A companion star may have disturbed the outer regions of the system. Another passing star within a young stellar cluster could have destabilized distant icy bodies. All of these are physically plausible mechanisms, supported by simulations and indirect observations elsewhere. Yet the present-day surface carries no simple marker that distinguishes whether the decisive push came from a giant planet, a binary companion, or a long chain of interactions. James Webb cannot see through the entire nucleus either. The coma contains only the material escaping during the period of observation. Regions receiving more sunlight contribute more gas, while deeper layers may remain untouched. If the nucleus is chemically heterogeneous, the measured composition at any given moment may represent one region more strongly than the object as a whole. Repeated observations help track changes as heat penetrates deeper layers, but the opportunity remains constrained by brightness, viewing geometry, and the limited time before the comet becomes too distant. Even the true size and shape of the nucleus are difficult to determine precisely while it is surrounded by gas and dust. Light from the coma can make the object appear far brighter than the solid body hidden at its center. To estimate its size, scientists must infer surface reflectivity, dust abundance, and activity levels. A darker surface would require a larger nucleus to produce the same brightness as a more reflective one. Uncertainty in each factor means results are typically expressed as ranges rather than exact values. The history of previous encounters with stars is equally difficult to recover. The outer layers may have been altered by cosmic radiation during the interstellar journey, but a close passage near another star could also have removed portions of the original ice. There is no certain way to know whether the Sun is the first star to awaken the object since it left its home system. Its unusual composition suggests that much of its ancient chemistry has survived, but it does not prove that the entire surface remained untouched. These limitations make the scientific picture less complete than a fictional narrative, but far more faithful to reality. In a story, a visitor might arrive carrying its birthplace, birth date, and full travel history. In nature, information usually survives only in fragments: an open trajectory, an isotopic ratio, an expanding cloud of gas, a velocity that does not belong to the solar system. The task of science is to connect those fragments using laws that can be tested, while remaining honest about what is still unknown. That caution protects discoveries from two opposite forms of exaggeration. One is the temptation to treat every unusual signature as something mysterious, beyond natural explanation. The other is the tendency to dismiss everything because some details remain uncertain. Both misunderstand how science actually advances. An interstellar origin can be established with high confidence, while the exact age remains only a range of possibilities. The chemical composition can be measured clearly, while the parent star remains unnamed. Different levels of certainty can coexist within the same investigation without contradiction. Webb is not working alone. Other telescopes on the ground and in space continue to track the object's position, brightness, coma structure, and changes over time. Data gathered in visible light, infrared, radio, or other wavelength ranges can complement one another. One instrument may be sensitive to a particular molecule, while another follows dust or the products left behind after sunlight breaks molecules apart. When many sources of observation are focused on the same object, the picture grows richer, and explanations that do not fit gradually fall away. Computer models help connect the data into possible histories. They simulate ice forming in cold clouds, disks around stars changing over time, isotopes becoming enriched, and planets throwing small bodies outward. Each model produces a set of results that can be compared with the observed spectrum. If many different conditions lead to the same signal, the uncertainty remains broad. If only one group of environments fits, the origin becomes more tightly constrained. A model does not replace observation. It is a way of testing which histories could have produced the data that has been measured. A mission that approached the object directly could answer many of the questions still left open, but interstellar visitors are often discovered only after they have already moved deep into the solar system, traveling at high speed. Preparing a spacecraft, launching it at the right moment, and catching up to the target would be an enormous challenge. Even a flyby would require a trajectory and launch energy calculated well in advance. Collecting a sample and bringing it back would be far more difficult. During this current passage, light remains the most practical way to reach that ancient material. Future encounters may be more favorable. If survey systems detect such objects earlier, humanity will have more time to plan observations and perhaps even prepare interception missions. A spacecraft flying past an interstellar object could photograph the nucleus clearly, measure dust and gas directly, and determine its shape, rotation rate, and surface activity. If an interstellar sample were ever returned to Earth, it would allow isotopic measurements with a precision far beyond remote spectroscopy and open an entirely new field in the study of planetary systems. For now, the value of 3I Atlas does not lie in having revealed its entire past. Its value lies in the fact that an otherwise unreachable object has left enough signals for multiple layers of history to become studyable. We know that it came from outside the solar system. We know that its ice carries chemistry, unlike that of familiar comets. We know that the data is consistent with an extremely cold environment and possibly a very ancient one. At the same time, science also knows that it has not identified the parent star, has not reconstructed the full journey, and has not seen the complete internal structure of the nucleus. The boundary of knowledge does not remain fixed. Each new observation can push it a little farther outward, yet beyond it there will always be regions that remain unclear. This is not a failure of the telescope, but the natural condition of studying an object that traveled for millions or billions of years before it was discovered. Light carries into the present only those parts of the past that were able to survive within it. In the months and years after this observation, the data will continue to be analyzed, compared, and placed into new models. Some estimates may narrow, some interpretations may change, and the strongest conclusions will remain. The object itself will grow more distant and fainter, but the light already collected will not disappear with it. Each spectrum becomes a record that scientists can return to, read with better methods, and search for signals that were once too subtle to notice. Webb has seen more than human eyes could ever see, but it has not seen everything. On this side of the boundary are the orbit, water, carbon, and unusual isotopic ratios. On the other side are the name of the star that gave birth to the object, the moment it was cast away, and every region of space it crossed. Between those two sides, science preserves a necessary emptiness, where the beauty of discovery comes not from absolute certainty, but from the ability to read part of an ancient story without pretending that the rest is already known. While those limits are carefully maintained, the visitor continues to move away. Sunlight weakens across its surface. The coma begins to thin, and the open trajectory carries it back toward a region where no nearby star will hold it. Humanity cannot follow it forever with every instrument, but what has already been recorded will remain, ready to close the brief encounter between a relatively young solar system and a fragment of matter that may have existed since a time when the Milky Way was very different from the one we know today. As scientists continue to read the spectra already collected, the interstellar object keeps moving farther away. Its path was bent by the sun during the encounter, but it did not close into a new orbit. Nothing in the solar system has enough force to turn this visitor into a long-term member. It will continue crossing the colder outer regions, move beyond the realm of the familiar planets, and gradually return to the dark, nearly silent state it carried through most of its life between the stars. As the distance grows, sunlight weakens across its surface. Heat stored in the shallow layers will continue escaping for a while, allowing some ice to keep sublimating even after the object has passed through its closest region. But that process will not last forever. The streams of gas will become thinner, the amount of dust lifted from the nucleus will decrease, and the coma that once helped telescopes see the object will begin to blend into the surrounding space. The faint tail will not be cut off in one clear moment. It will simply grow more diffuse, more delicate, until there is no longer enough reflected light to separate it from the background sky. Beneath the disappearing gas, the nucleus still carries a large amount of ice that has not been opened. The sun only awakened regions close enough to the surface for heat to reach during this passage. Deeper layers remain still, preserving water, carbon dioxide, and many other compounds that never appeared in the data. That material may be even more primitive than what Webb has seen, or it may have followed a different history within the same nucleus. Humanity will not know all of it, because the comet will not return to offer a second opportunity under the same conditions. That lack of return makes this encounter different from the familiar comets of the solar system. A comet held by the sun may appear again and again, allowing generations of telescopes to compare its activity across multiple orbits. Its surface changes, its active regions shift, and new instruments may see more deeply than the ones before. An interstellar visitor opens only a single window. Whatever is not recorded during that interval will continue beyond reach along with it. Even so, the encounter does not end the moment the point of light becomes too faint. The data already collected will be studied for a long time. Each spectrum contains more layers of information than can be read at first glance. As processing methods improve, researchers can return to older measurements, search for weak signals once hidden by noise, or compare them with newer and more accurate models. An object that has left the observing window can still produce discoveries through the light it left behind. Astronomy has advanced this way many times before. A data archive does not serve only the moment in which it is created. Old measurements can be reopened when a similar phenomenon appears, when another telescope provides a comparison sample, or when new theory makes previously unclear details meaningful. For this visitor, isotopic ratios, the distribution of gas in the coma, and the level of activity at different distances will become reference points for interstellar objects discovered in the future. The fourth object may carry a composition closer to comets in the solar system. The fifth may be even more different. Some may come from young star systems, some may be born in regions rich in heavy elements, and others may preserve traces of a very early period in the history of the Milky Way. Each encounter will not stand alone. Together, they will gradually form a library of planetary systems humanity cannot yet approach. For now, that library has only a few pages. 3 confirmed interstellar objects are not enough to describe the vast population that exists between the stars. Most free fragments of ice and rock probably never pass close enough to a source of light to become easy to see. Some sweep through the solar system at distances too great to detect, while others are so small that their reflected light never rises above the limits of our instruments. The visitors we recognize are only a tiny portion of a quiet stream of material moving through the galaxy. Future survey systems will be able to see more of them and see them earlier. An object discovered while still very far away gives astronomers more time to prepare, to follow its activity from the first moment the ice begins to respond, and to continue observing as it moves inward and then back out from the star. A longer chain of data can distinguish surface material from deeper layers released later, while also providing a more precise orbit for studying its dynamical origin. If an interception mission is ever prepared in time, humanity may be able to see an interstellar object from much closer range. A spacecraft flyby could directly measure gas, dust, magnetic fields, and the shape of the nucleus. Cameras could reveal cliffs, fractures, active vents, and patterns of light and darkness across the surface. In situ measurements would test conclusions drawn from spectroscopy and show how a comet has changed after a long journey outside every planetary system. Returning a sample is more distant still, but it no longer lies completely outside scientific imagination. A few grains of dust collected from a coma could contain isotopic ratios measured with far greater precision than remote observations allow. In a laboratory, individual organic molecules, mineral structures, and ancient ice layers could be analyzed separately. A small sample from another star system would let humanity place solar system material beside extrasolar material in the most direct way possible. But even before that day arrives, this encounter has already changed an old boundary. In the past, other planetary systems appeared mainly through the light of their stars and the shadows of planets passing in front of them. Now, a piece of material belonging to somewhere else has entered a region where humanity can examine its composition in detail. The distances between star systems remain immense, but matter sometimes crosses those distances on its own, without any spacecraft ever leaving Earth. There is a gentle contrast in the way this encounter unfolds. The object may have traveled through billions of years, yet the period in which it appears clearly in human data is very brief. It may have crossed eras during which the Milky Way changed its structure. Many generations of stars were born and disappeared, and the solar system formed from a cloud that did not yet exist when this ice first began to take shape. And yet most of what humanity knows about it comes from a small number of observations when sunlight passed through its expanding cloud of gas. The length of a history does not necessarily determine the size of the trace it leaves behind. A very ancient object may appear only as a faint point of light. An important difference in its birth environment may lie in the ratio between two forms of an atom that are almost identical. A rare encounter in the galaxy may occur without changing anything in daily life on Earth. The event does not need to be loud to matter. Its meaning comes from our ability to recognize the small. As the visitor continues to recede, the solar system itself appears in a slightly different way. Our home around the sun is often imagined as a relatively closed structure, with planets and comets sharing a common origin. But the orbit of this interstellar object shows that the boundary can be crossed. Material from elsewhere can enter, and fragments born here may also have been thrown outward by the planets and set adrift through the Milky Way. Perhaps even now, a comet that once formed around the sun is moving through the darkness between stars, carrying the water and carbon ratios of the disk that created Earth. It may never encounter another planetary system, or, after millions of years, its path may bring it near a distant star, where its ice begins to sublimate, and some observer recognizes that it does not belong to their home. In this way, planetary systems are not completely isolated, even though the distances between them remain almost impossible to cross on the scale of human life. Each ejected object carries a small sample of its old environment. These fragments do not exchange matter in a steady or directed flow, but across immense spans of time, The Milky Way may contain countless pieces of debris from many different star systems. These free comets are leftovers of planet formation, materials not kept in stable orbits but not destroyed either. They continue to exist, carrying the chemical histories of distant systems through regions of space that belong to no single star. The visitor that has just passed through has given humanity one glimpse into that slow exchange. It does not carry the full story of its parent system, but it is enough to show that matter can survive an interstellar journey and still retain part of its original signature. Cold preserves some molecules, the nucleus shields deeper layers, and time, though it alters the surface, does not erase everything. When the sun awakens the ice, that chemical memory appears again in an environment entirely different from the one that created it. The encounter also reveals humanity's unusual role in the story, not as the center of the universe, but as a species capable of recognizing very small signs. On a planet orbiting a relatively ordinary star, telescopes have been built to collect light invisible to the eye, split it into spectra, and search for subtle differences in isotopic ratios. No one was present when the ice formed. No one saw the moment it was thrown from its parent system. Yet part of that history can still be reconstructed from physical laws preserved in matter. That level of understanding remains limited, and it may change as new data appears. An extremely ancient age is still a possibility, supported by chemical evidence, not a birth date that has been confirmed with absolute certainty. The formation environment is described through constraints, not as a specific location. That caution does not lessen the beauty of the discovery. It keeps the story at the right distance between what is known and what remains open, where curiosity does not need exaggeration to survive. As the coma gradually fades, the object reveals less than it did before. The gas that once carried the signatures of heavy water and ancient carbon is stretched outward and dispersed. The nucleus continues on, growing cold again and carrying layers that have never been seen. The sun recedes behind it, becoming only one star among the many it may pass in the future. There is no sign to tell us when a similar encounter will happen again, or whether the object will ever be recognized by any observing civilization. For the solar system, all the familiar motions continue. Earth orbits the sun, the planets follow their paths, and native comets remain in the cold, distant regions. This passage leaves no major disturbance in that structure. What changes is the way humanity looks at its home. The solar system is no longer compared only with distant points of light. It has now received a real fragment of matter from somewhere else. The object will leave, but its light has been preserved. In those delicate spectra, an ancient cold environment, an early era of the Milky Way, and a lost planetary system still remain as data. The numbers are quiet and incomplete, but they are enough to expand the history that humanity can touch. Not every visitor needs to stay long to change how we see our home. Sometimes a fragment of ice only passes through a region of light, leaves a few traces in that light, and continues on. And when darkness closes around it once more, what remains is not only a deeper understanding of an ancient comet, but also the feeling that across the immense distances of the galaxy, distant worlds can still send one another small pieces of memory without ever knowing it.